What if everything we know about the universe is merely a fragment of something far grander? The observable universe, the area we can see and measure, stretches across mind-boggling distances, yet it remains limited by the fundamental boundaries of light and time. But what lies beyond this visible expanse? Are there unknown cosmic structures, or perhaps entirely different dimensions, waiting to be uncovered? Join us as we venture through space, seeking to answer this profound question. What truly lies at the very edge of our universe? The observable universe is not an all-encompassing concept, but rather a boundary defined by the limits of what we can observe from our vantage point on Earth. Picture it as a vast, ever-expanding balloon with us positioned at a point on its surface. The further we look into the distance, the more we realize that the universe we can see is just a small window into something far greater. At its core, the observable universe is determined by the distance that light has traveled since the beginning of time. This starting point is what we often refer to as the Big Bang. Because light travels at a finite speed, it takes time for light emitted by distant objects to reach us, meaning we are looking back in time, not simply out into space. Over the course of billions of years, the light from countless stars, galaxies, and other celestial phenomena has slowly made its way across space to us, forming a spherical shell of observable points around our position in the universe. The furthest we can currently see lies at the edge of this shell, marking the limit of the universe as we know it. This boundary, though vastly large, only contains light that has had time to travel to us from the very beginning. But this boundary does not signify the end of the universe itself. It simply marks the furthest point we can observe. Beyond it, the universe may continue indefinitely, teeming with galaxies, cosmic events, and phenomena that remain beyond our comprehension. As the universe continues to expand, the observable universe shifts too. This constant evolution allows us to see deeper into space over time, as light from even more distant objects continues to reach us. And so, the observable universe is not a static feature. It is ever-changing, shaped by the dual forces of time's relentless march and the growing sophistication of our technological capabilities. Astronomers, in their quest to unravel the mysteries of the cosmos, have developed a sophisticated set of techniques to chart the universe from our location on Earth. To fully grasp the vastness of space and the limitations imposed by our planet's atmosphere, scientists rely on various tools and methods. The atmosphere, while essential for sustaining life, also acts as a barrier to our observations. It scatters light and absorbs specific wavelengths, limiting what our telescopes can detect. For example, without specialized equipment, we are blind to certain parts of the electromagnetic spectrum, such as ultraviolet and infrared light. One critical technique for mapping the heavens is the use of celestial coordinates, a system that allows astronomers to pinpoint the location of stars and other objects in the sky. This system functions much like the latitude and longitude grid on Earth, enabling astronomers to track the movement of celestial bodies over time and predict when and where particular stars or galaxies will be visible. This system allows for precise observations and comparisons across different times and locations, contributing to a deeper understanding of the cosmos. Telescopes, both ground-based and spaceborne, are equipped with a variety of instruments designed to capture a wide range of wavelengths of light. From the low-frequency radio waves to the more familiar visible light, and even into the infrared and ultraviolet spectrums, each wavelength reveals different aspects of the objects we observe. For example, some distant galaxies shine brightly in infrared light, which is invisible to the naked eye, but crucial for understanding their structure and behavior. By analyzing these different wavelengths, astronomers can uncover information about the composition, distance, tethyer, and even the history of distant cosmic phenomena. Advanced computer models and simulations also play an important role in our understanding of the universe. These simulations account for a multitude of factors, such as the Earth's rotation, our orbit around the Sun, and even the gravitational interactions between stars and galaxies. With this data, astronomers can predict the future positions of celestial objects and the way they will be visible from Earth. Over time, these simulations have allowed scientists to create detailed catalogs that track the movement and brightness of stars and galaxies. This collection of data is indispensable to both professional astronomers and amateur stargazers, as it helps to predict what will be visible at any given time and location on our planet. Despite our advancements in observation, the sheer scale of the universe poses substantial challenges. The distances between celestial objects are so immense that even the most powerful instruments available today can only capture a fraction of the light that reaches us. Many stars and galaxies are so far away that the light we see from them today may have traveled for millions or even billions of years, meaning we are seeing them as they existed in the past, not as they are now. This presents a significant obstacle for obtaining real-time data about the current states of these objects. Our telescopes also face limitations when it comes to the wavelengths of light they can detect. While we can observe the universe in visible light, there are entire realms of radiation that remain hidden to our eyes. For instance, many significant cosmic events, such as supernovae or the formation of new stars, often take place in wavelengths beyond the visible spectrum, such as infrared light. To study these phenomena, astronomers require specialized telescopes designed to detect this radiation, which means much of the universe's activity remains invisible to our conventional instruments. Additionally, the atmosphere itself poses an ongoing challenge for astronomers. The Earth's atmosphere distorts the light that passes through it, blurring images and limiting the precision of our observations. To minimize these effects, astronomers have built observatories at high altitudes or in regions with particularly clear skies. Space telescopes like the Hubble Space Telescope have revolutionized our ability to observe the cosmos by removing the distortive effects of the atmosphere. However, even these instruments are not immune to the passage of time. Space-based telescopes have finite lifespans and are limited in the perspectives they can offer, providing only a glimpse into the vastness of the universe. Yet despite these challenges, our thirst for knowledge continues to drive us forward. As technology advances and our understanding deepens, we may one day uncover the answers to the greatest questions about the universe's true nature. What lies beyond the observable universe? How far does the universe extend? And is it really as infinite as it seems? These are questions that may take us a lifetime or even several lifetimes to answer. But with each breakthrough in science and each advancement in technology, we edge ever closer to unraveling the mysteries of the cosmos. The sheer scale of data processing and storage capacities has become a crucial aspect of modern astronomical research. The amount of information that is collected by advanced telescopes today is truly staggering. As our technological abilities continue to push the boundaries of space exploration, the processing power required to handle this vast influx of data has begun to exceed the limits of our current computing resources. Every time a telescope observes the cosmos, it gathers an overwhelming amount of data, from high-resolution images to complex spectroscopic readings, all of which must be processed and analyzed swiftly. Yet, despite these incredible advancements in observation technology, the task of drawing meaningful conclusions quickly remains a significant challenge. With each leap in the sophistication of space observation, the need for increasingly advanced algorithms and larger storage solutions becomes ever more critical. As our telescopes collect more detailed data from the farthest reaches of space, the demands on data storage and computational power escalate. This evolving technological landscape is a double-edged sword. While our ability to observe distant galaxies, supernovae, and other cosmic phenomena grows exponentially, our capacity to analyze and understand these observations quickly lags behind. Therefore, data handling becomes as much a frontier as the exploration itself. But the challenges do not end with just data processing. There are other crucial limitations that shape our observations of the universe. One of the most formidable challenges is the sheer distance between us and the celestial objects we seek to study. No matter how advanced our telescopes become, they can only capture light that has traveled across unimaginable expanses of space and time. And yet, this is but one hurdle. The range of wavelengths we can detect is also a significant limitation. Our telescopes are bound by the types of radiation they can capture. Whether it's visible light, infrared, the ultraviolet, or radio waves, each offering a different slice of the cosmic puzzle. Atmospheric interference further complicates matters. Earth's atmosphere, while essential for sustaining life, also acts as a barrier to certain wavelengths of light, especially in the case of optical telescopes. This interference can blur the clarity of observations, rendering fine details of distant galaxies, nebulae, and stars impossible to discern with complete precision. Hence, many of the most powerful telescopes are now positioned above the atmosphere, on satellites and space stations, to avoid such distortions and gain a clearer view of the universe. Despite these many hurdles, scientists are constantly striving to overcome these challenges in their quest to unravel the mysteries of the cosmos. It is within this pursuit that the cosmic microwave background radiation, CMB, plays an integral role. The CMB is often described as the faint, ancient glow left behind from the early universe, a critical piece of the cosmic puzzle. This radiation serves as a relic from a time just after the Big Bang, offering us a unique snapshot of the universe in its infancy. To visualize the significance of the CMB, imagine the universe as a balloon being inflated. Initially, the universe was extremely hot and dense, filled with energetic particles and radiation. As the universe began to expand, it cooled down, allowing the formation of atoms. This cooling marked a crucial moment in cosmic history. About 300,000 years after the Big Bang, the universe became transparent to radiation for the first time. The cosmic microwave background is the residual glow from this era, which has since stretched and cooled to much lower temperatures as the universe expanded. As the universe continues to expand, the CMB fills the cosmos, providing a uniform backdrop of faint light. This light is not just a relic of the past. It offers essential clues about the early conditions of the universe, including its temperature, density, and the distribution of matter and energy. By studying tiny fluctuations in the temperature of the CMB, scientists can trace the beginnings of cosmic structures, such as galaxies, galaxy clusters, and vast cosmic voids. These fluctuations reveal the seeds of the universe's complexity, offering insight into the growth of these structures over billions of years. The study of these temperature variations within the CMB is akin to peering into a cosmic blueprint, revealing vital information about the universe's early composition and expansion. By analyzing these minute variations, astronomers can begin to reconstruct the conditions that gave rise to the galaxies and other cosmic structures we observe today. Additionally, this radiation holds the keys to understanding some of the most profound questions in cosmology, such as the nature of dark matter, dark energy, and even the ultimate fate of the universe. In essence, the CMB serves as a cosmic fingerprint, offering a record of the universe's birth and a glimpse into its future. By studying this ancient glow, we gain a deeper understanding of the cosmos's evolution and the forces that shape it. Each new observation enriches our knowledge, bringing us one step closer to unlocking the mysteries of the universe, from its chaotic inception to the complex, interconnected system we observe today. Telescopes in this context are our cosmic eyes. They serve as instruments that peer into the vastness of space, uncovering secrets hidden in the dark corners of the universe. To imagine a telescope is to imagine standing in a dark room, using a flashlight to illuminate hidden details. This is the essence of a telescope's purpose, collecting light across vast distances and from objects too distant to be seen by the naked eye. Whether it is visible light, radio waves, or infrared radiation, telescopes enable us to observe celestial bodies far beyond our solar system, revealing a universe filled with far more than we could ever have imagined. The technology behind telescopes has evolved dramatically over the centuries. Early optical telescopes relied on lenses and mirrors to magnify the light from distant objects. These instruments, while groundbreaking in their time, could only reveal so much. The development of more advanced telescopes capable of detecting light across a broader range of wavelengths has significantly expanded our understanding of the cosmos. For example, infrared telescopes allow us to observe objects obscured by dust, while radio telescopes reveal hidden features of distant galaxies. One of the most exciting advancements in telescopic technology is the ability to observe the faint glow of cosmic microwave background radiation. These specialized instruments offer unprecedented insight into the universe's birth and evolution. For instance, by analyzing the patterns within the CMB, scientists can trace the expansion of the universe, map the distribution of galaxies, and gain clues about the forces that have shaped the universe's growth over billions of years. Moreover, telescopes positioned outside Earth's atmosphere, such as the Hubble Space Telescope, offer a clearer view of distant objects, free from the atmospheric distortion that plagues ground-based observatories. These space-based telescopes allow astronomers to observe faraway galaxies, stars, and nebulae with far greater clarity and accuracy. By mapping the structure of the universe in greater detail, these instruments contribute to our understanding of cosmic phenomena, including supernovae, black holes, and the mysterious substances, dark matter and dark energy, that influence the universe's expansion. As telescopes continue to push the boundaries of what is observable, they not only shed light on the universe's past, but also guide us in our search for distant worlds. The study of distant exoplanets, the search for signs of life beyond Earth, and the ongoing quest to understand the fundamental forces that govern all existence are all part of this grand adventure. Through the lens of these powerful instruments, we continue to explore the unknown, unveiling the story of the cosmos one discovery at a time. The expansion of the universe plays a pivotal role in how we perceive the light we receive from distant galaxies. As the universe stretches, so too does the space between galaxies. This stretching of space causes the wavelengths of light traveling through it to elongate, a phenomenon known as redshift. As galaxies recede from us, the light they emit is stretched, making it appear redder than it actually is, just as the pitch of a passing car's horn lowers as it moves away. This redshift is not only an indicator of a galaxy's velocity, but also provides insight into the very history of the universe. The light from distant galaxies has traveled across vast expanses of space and time, offering us a unique window into the past and a glimpse into the ongoing evolution of the universe itself. Moreover, the ongoing expansion of the universe profoundly shapes the way we perceive the cosmos. There are galaxies out there whose light will never reach us, no matter how advanced our technology becomes, because they are receding at speeds faster than light itself can travel through the ever-expanding space between us. This phenomenon places a natural limit on the observable universe, meaning that we can only access a fraction of everything that exists. The further we peer into the distance, the further back in time we are looking, revealing the universe as it existed in its infancy. This glimpse into the universe's youth provides essential clues about its development over the ages. The expansion of the universe is not just a passive background event. It directly influences the ultimate fate of the cosmos itself. And depending on the density of matter and energy it contains, the expansion might either accelerate indefinitely or slow down over time. This dynamic process, constantly changing and evolving, forms the basis of our understanding of the universe's fundamental properties, such as its shape and the fundamental forces that govern its behavior. It is no exaggeration to say that the study of cosmic expansion is indispensable for anyone seeking to grasp the true nature of existence. Satellite missions have been at the forefront of expanding our understanding of the universe, particularly in terms of its boundaries and the defining phenomena that characterize these limits. One of the most remarkable contributions has been the study of cosmic background radiation, which serves as a faint but reliable echo of the Big Bang itself. This faint glow, detectable even today, provides crucial insights into the early stages of the universe and helps define both its age and extent. Missions such as the Wilkinson Microwave Anisotropy Probe, WMAP, have meticulously mapped this radiation, revealing the large-scale structure of the universe and offering an invaluable snapshot of its early days, when the cosmos was just a few 100,000 years old. Furthermore, these missions have allowed astronomers to extend their gaze far beyond our Milky Way. The Hubble Space Telescope, for instance, has delivered breathtaking images and data, providing a window into galaxies that lie billions of light years away. These observations are crucial, as they allow us to measure the rate of the universe's expansion and estimate the scale of the observable universe. Thanks to the Hubble Space Telescope, we can see galaxies and cosmic phenomena from an era long before the Earth even existed. In addition to these optical and infrared observations, recent breakthroughs in gravitational wave astronomy are reshaping our understanding of the universe's extremes. These ripples in the fabric of spacetime, caused by catastrophic events such as black hole mergers, have opened up an entirely new way of studying the cosmos. Gravitational waves allow us to probe violent and otherwise invisible phenomena that take place in the farthest reaches of the universe, revealing insights into its most extreme environments. The continuous flow of data from these satellite missions also sheds light on some of the most mysterious and elusive components of the universe: dark matter and dark energy. Together, these invisible forces are believed to make up approximately 95% of the universe, yet their exact nature remains one of the greatest unsolved puzzles in modern science. By studying the effects of dark matter and dark energy, scientists are hoping to unlock the mysteries of how the universe is structured and what forces will ultimately determine its fate. These missions act as our most advanced eyes, pushing the frontiers of human knowledge ever further into the depths of the cosmos. Each launch of a new space mission not only enhances our understanding of the universe, but also raises new questions that stimulate the curiosity of astronomers, cosmologists, and even the general public. Every discovery opens new avenues of inquiry, fueling the search for answers to the fundamental questions about the nature of existence. A core concept in the study of the universe is redshift, a phenomenon that plays a vital role in how we measure the scale of the cosmos. Redshift occurs when the wavelength of light from distant objects is stretched out as the universe expands. The further a galaxy moves away from us, the more its light is stretched toward the red end of the electromagnetic spectrum. To visualize this, imagine holding a rubber band and pulling it. Just as the rubber band stretches, so too does light when the source moves away from us. This stretching of light waves, known as redshift, is a powerful tool for astronomers. By measuring how much the light from distant galaxies has been redshifted, scientists can determine the speed at which those galaxies are receding from us. This relationship between distance and velocity allows astronomers to build a cosmic map that stretches across vast distances, showing not just our local neighborhood in the universe, but also galaxies billions of light years away. The study of redshift has provided a key insight into the universe's expansion and is central to understanding its overall structure. Redshift has helped scientists measure the distances to galaxies that are so far away that their light has traveled for billions of years to reach us. These measurements are crucial for exploring the origins of cosmic phenomena, such as the formation of galaxies and stars, as well as the ultimate fate of the universe itself. By using redshift as a gauge, astronomers have been able to piece together a detailed picture of the universe's size, shape, and expansion rate. As such, redshift has become a cornerstone of modern astrophysics and cosmology, central to our understanding of the cosmos. However, as we peer deeper into the vastness of space, we are limited by what we can see. The observable universe is the portion of the universe that is within our reach, but beyond this boundary lies an unknown expanse, one that challenges our understanding of what is and isn't accessible. Several theories attempt to explain what might lie beyond the observable universe, pushing the boundaries of our imagination. One prominent theory suggests that the universe extends far beyond what we can observe, possibly stretching infinitely. Just as the surface of an ocean appears limitless from the perspective of a small boat, the universe might stretch endlessly, containing an infinite number of stars, galaxies, and possibly even regions where the laws of physics operate differently than they do in our own observable universe. This idea implies that there are parts of the cosmos that we may never be able to access or observe, simply because they exist beyond the horizon of our current capabilities. The concept of the multiverse takes this idea even further, positing that our universe is just one of many, each existing within its own bubble. Imagine a pot of boiling soup, with each bubble representing a separate universe. Some of these universes might have properties and physical laws that are remarkably similar to our own, while others might be drastically different. Some could have different dimensions of space and time, or even entirely different fundamental particles and forces. This multiverse theory could also be explained through the framework of cosmic inflation, a period of rapid expansion that occurred just moments after the Big Bang. According to some interpretations of inflation theory, the visible universe we inhabit is just one bubble in a vast and ever-expanding sea of space, with other universes forming simultaneously in a constantly bubbling cosmic expanse. If this theory holds true, the nature of the cosmos becomes even grander, a complex tapestry interwoven with countless realities, each with its own set of properties and conditions. There are also ideas that propose a more complex geometry, one that exists beyond the boundaries of our perception. Imagine a landscape that stretches beyond the horizon, a place where the physical laws we take for granted may operate in ways we cannot yet comprehend. This opens up the possibility of entirely new structures, phenomena, and cosmic principles that challenge our current understanding of the universe. Although these ideas are fascinating, they remain speculative. Our current understanding of physics and the cosmos is still in its infancy, and direct evidence for many of these concepts remains elusive. However, such theories encourage us to think beyond the limits of what we know and to explore the boundless mysteries that still await discovery. The very idea that there could be so much more beyond the observable universe challenges not only our scientific knowledge, but also our philosophical assumptions about the nature of existence. In essence, the multiverse theory represents a paradigm shift in how we view the cosmos. It forces us to reconsider the nature of reality itself, suggesting that our universe might not be the only one, and perhaps not even the most unique. It raises profound questions about the origins of our universe, the possibility of infinite variations of existence, and the very fabric of reality. What if our universe is merely one thread in a vast cosmic tapestry, each thread representing a separate universe, each with its own story to tell? The pursuit of answers to these questions may ultimately reshape our understanding of the cosmos and our place within it. The concept of the multiverse fundamentally reshapes our understanding of reality and challenges the conventional way we think about the universe. It invites us to reconsider the very nature of causality and randomness, suggesting that events which seem utterly unpredictable or even impossible in one universe may unfold differently in another. This idea isn't confined merely to scientific inquiry. It spills over into philosophy, forcing us to grapple with questions of choice, destiny, and consciousness in a way we've never done before. If there are countless other universes out there, each with its own set of laws and possibilities, what does that mean for our understanding of existence and the decisions we make? Though the multiverse remains largely theoretical, lacking concrete observational evidence, it pushes the boundaries of scientific exploration and philosophical debate. Cosmologists and thinkers from many fields are not just peering into the cosmos we can see, but are also speculating about realms that might be beyond our observational reach. In doing so, they open up an almost limitless expanse of possibilities, an infinite horizon of cosmic landscapes that could dramatically alter the way we understand existence. At the heart of this vast mystery lies the theory of cosmic inflation, a key concept in modern cosmology that helps unlock the secrets of the universe's earliest moments. Imagine a universe so young that it was just a fraction of a second old, smaller than a single atom. During this brief and explosive period, the universe expanded at an astonishing rate, far faster than the speed of light. This rapid inflation is more than just an interesting fact. It helps explain some of the most fundamental properties of the cosmos. For example, it addresses why the universe looks so uniform on large scales today. Without inflation, distant regions of the universe would have been so far apart that they could never have influenced one another, resulting in a cosmos that looks vastly different than what we observe now. The swift inflationary phase brought together areas of space that would have otherwise remained isolated, smoothing out temperature and density differences across the universe. This uniformity is observed today as the cosmic microwave background radiation, a faint glow that fills every corner of the universe, echoing the conditions of the universe's infancy. Moreover, cosmic inflation challenges our very conception of the universe's boundaries. It suggests that the observable universe is but a small region of a much larger, potentially infinite expanse. Beyond what we can currently perceive may lie entirely different regions of space, governed by laws and phenomena that we've yet to imagine. This idea suggests that the universe could be boundless, an endless stretch of cosmic possibilities, and what we see might only be a fraction of the whole. The fluctuations caused during inflation also have significant long-term consequences. These tiny variations in the density of matter that occurred during inflation would, over billions of years, grow into the galaxies, stars, and cosmic structures we observe today. The formation of the universe's large-scale structures is directly tied to these minute irregularities, which acted as seeds for the development of everything we see in the cosmos now. Cosmic inflation is, therefore, not just crucial for understanding the early moments of the universe's birth. It also plays a pivotal role in shaping our perception of the universe's boundaries and composition. This groundbreaking concept reveals that the universe is far more vast and complex than our current understanding suggests, urging us to reconsider not just the scope of the cosmos, but also the possibility of multiple universes beyond our reach. String theory offers a compelling perspective on the fundamental makeup of the universe, particularly when it comes to its structure and boundaries. Unlike the traditional view, which holds that the universe's building blocks are tiny, point-like particles, string theory proposes that these building blocks are, in fact, tiny, vibrating strings. These strings oscillate in various patterns, producing the myriad particles that form the material world around us. At the edges of our observable universe, string theory offers a multidimensional framework where the familiar 3 dimensions of space and 1 dimension of time are not the full picture. In string theory's view, there could be additional dimensions, hidden from our perception, that are curled up or otherwise inaccessible to our senses. These hidden dimensions could dramatically alter our understanding of space itself, and perhaps even provide clues to the expansion of the universe. In string theory, the universe is not a finite, clearly defined entity, but is instead a vast fabric that could extend into higher dimensions where the usual laws of physics might operate differently. This concept opens up exciting possibilities. Perhaps the universe is infinite, looping back on itself in some mysterious way, or perhaps it is even connected to other universes, forming a larger interconnected multiverse. Moreover, string theory encourages a rethinking of other phenomena, such as black holes and cosmic inflation, suggesting that these processes might be influenced by these hidden dimensions. This interconnectedness of dimensions could reveal much about the origins of the universe and how it continues to evolve. Instead of seeing the universe as a structure with sharp boundaries, string theory helps us envision a cosmos where the edges are not well defined, but rather exist as smooth transitions into realms where the laws of physics behave in ways we cannot yet comprehend. Through the lens of string theory, researchers are no longer only peering into the outer reaches of the cosmos, but are also investigating the very laws that govern the fabric of reality itself. This approach challenges our understanding of existence, questioning the limits of the known and the very nature of reality as we understand it. Meanwhile, quantum mechanics, the branch of physics that governs the behavior of the smallest particles in the universe, also plays a crucial role in our understanding of the cosmos. Though it may seem distant from the vastness of space, quantum mechanics has a profound influence on the evolution of the universe. One of the most fascinating concepts in quantum mechanics is quantum fluctuations, which refer to the tiny, unpredictable changes that occur even in the vacuum of space. Far from being empty, space itself is teeming with activity, with particles appearing and disappearing in a never-ending dance of uncertainty. This phenomenon has wide-reaching implications for the universe. For instance, during the moments immediately following the Big Bang, quantum fluctuations may have had a profound impact on the distribution of matter and energy across the cosmos. These fluctuations could have influenced the way galaxies, stars, and other cosmic structures formed, playing a fundamental role in shaping the universe as we know it today. Thus, the quantum world, though invisible and distant from our everyday experience, has played an instrumental role in the very evolution of the universe, influencing its structure, its history, and its future. In many ways, it's the unpredictability and the strange, almost mystical behavior of quantum mechanics that continues to challenge and fascinate scientists as they probe the very building blocks of reality. Together, the ideas of the multiverse, cosmic inflation, string theory, and quantum mechanics paint a picture of the universe that is far more complex and interconnected than anything we might have imagined. Each theory offers a new lens through which to view the cosmos, expanding our understanding and challenging the limits of our knowledge. As we continue to explore these ideas, we push the boundaries of human understanding, reaching for new horizons in both science and philosophy. Moreover, quantum entanglement offers a fascinating and perplexing insight into the fabric of reality. When particles become entangled, their states are intricately linked in such a way that the condition of one particle is instantly connected to the state of another, no matter how far apart they are. This relationship defies our traditional understanding of locality, suggesting that information may travel across vast distances of the cosmos in ways we have yet to fully grasp. Such connections raise profound questions about the true nature of space, time, and the very structure of the universe. Could these entangled particles hint at a deeper, unified truth? Perhaps this mysterious phenomenon could force us to revise our fundamental concepts of reality itself, offering new perspectives on the interplay of forces that govern the universe. In the realm of black holes, quantum mechanics and general relativity often clash in a spectacular confrontation. One of the most perplexing questions is the fate of information that falls into a black hole. When matter crosses the event horizon of a black hole, what happens to the information that defines its properties? Classical physics suggests that information might be lost, but quantum theory firmly rejects this idea. According to quantum mechanics, information cannot simply vanish, setting the stage for a theoretical conflict that requires entirely new frameworks to resolve. The clash of these two great pillars of physics, quantum mechanics and general relativity, has yet to be fully reconciled, and understanding what occurs at the heart of a black hole may hold the key to unlocking entirely new dimensions of knowledge. Another intriguing possibility stems from the multiverse hypothesis, which is deeply rooted in quantum mechanics. This theory proposes that at every quantum decision point, where particles behave in a variety of unpredictable ways, a new universe is born, branching off from our own. The concept of the multiverse introduces the idea of an almost infinite collection of parallel universes, each with its own distinct physical laws and outcomes. These universes could be radically different from ours, existing side by side in an ever-expanding cosmic landscape. The multiverse theory pushes the boundaries of our imagination, suggesting that the reality we experience is just one of countless others that may be governed by entirely different principles. In this view, quantum mechanics not only illuminates the intricate workings of the cosmos, but also challenges our most fundamental assumptions about the nature of reality. Moreover, the concept of wormholes has become an essential component in exploring the unknown corners of the universe. Imagine a wormhole as a tunnel that connects two distant points in space, providing a shortcut through the fabric of space-time. If such tunnels exist, they could offer the potential to travel between galaxies, or even through different points in time. The very existence of wormholes challenges our conventional understanding of the universe. These shortcuts might provide access to hidden regions of space, allowing us to explore dimensions and realities beyond the reach of our current technology. The thought of traversing such cosmic highways invites speculation about what might lie beyond the observable universe, areas that remain hidden from our direct observation. Wormholes also open up fascinating questions about the nature of dark matter and dark energy, two mysterious entities that constitute a significant portion of the universe's total mass energy, but remain completely invisible. If wormholes exist, could they interact with these unseen forces in ways that we have yet to comprehend? Such theoretical exploration could offer a new understanding of how dark matter and dark energy influence the visible universe. These hidden realms could shape the overall structure of space-time, offering insights into how the traditional laws of physics might break down or behave differently in distant regions of the cosmos. As speculative as it may be, the idea of wormholes continues to inspire scientific inquiry and challenges us to think beyond the known limits of space and time. This line of thinking intersects with a concept first derived from the study of black holes, which has led scientists to an intriguing realization. The universe itself might function in a way similar to a hologram. Imagine that the vast and complex universe we observe in 3 dimensions, filled with galaxies, stars, and planets, could be encoded in a simpler 2-dimensional format, much like a movie projected onto a screen. This idea is rooted in the discovery that the amount of information contained within a black hole is proportional not to its volume, as one might expect, but to its surface area. This groundbreaking revelation sparked the hypothesis that our entire universe may operate in a similar manner, where the full complexity of 3-dimensional reality is actually encoded on a distant 2-dimensional boundary, effectively separating our universe from the void that lies beyond. If we accept this holographic principle, it suggests that there could be limits to the amount of information the universe can contain. In essence, it proposes that the universe may have a cosmic data cap. This idea challenges the fundamental assumptions about the nature of space and time, raising critical questions about the very essence of reality. Are there hidden boundaries to what we can observe or understand? What happens at the edges of our known universe, where information may be constrained or lost entirely? This perspective encourages scientists to explore a deeper layer of existence, one that remains invisible to our everyday experiences. It offers an invitation to rethink what we know about the scale, substance, and potential limitations of the universe. Dark energy, an enigmatic force that has profound implications for the expansion of the universe, plays a crucial role in shaping the cosmos. To visualize dark energy's influence, imagine the universe as a balloon being inflated. As air fills the balloon, the surface expands, causing galaxies to move farther apart. This process of cosmic expansion is driven by dark energy, which is thought to constitute a substantial portion of the universe's total energy content. However, while we can observe the expansion of distant galaxies, many parts of the universe remain completely beyond our reach, hidden from our view. Dark energy, however, is not confined to only the regions we can observe. It permeates the entire universe. Even the farthest reaches, where no light or matter can be detected, experience the effects of dark energy. This hidden influence of dark energy affects not only the observable universe, but also regions that lie beyond our direct observation. As these invisible areas expand, they contribute to the overall evolution of the universe, shaping its structure in profound ways. Furthermore, dark energy is believed to accelerate the rate at which the universe is expanding, causing more distant regions to recede from us at ever-increasing speeds. This discovery forces us to rethink our understanding of cosmic history, suggesting that the universe's expansion is not just a static process, but an accelerating phenomenon. In this context, dark energy is more than just a mysterious force. It is a key player in shaping the ultimate fate of the cosmos. Cosmic voids and superclusters, 2 large-scale structures in the universe, offer crucial insights into the overall organization of the cosmos. Picture the universe as a vast ocean, with cosmic voids representing the empty spaces between clusters of galaxies. These voids, often spanning millions of light years, are regions of near-complete emptiness, with fewer galaxies and much cooler temperatures. They are vast, dark expanses, lacking the activity and density found in other parts of the universe. In stark contrast to these voids are superclusters, massive groups of galaxies bound together by the force of gravity. These superclusters are dense, bustling areas filled with galaxies, stars, and other celestial bodies. When scientists observe the universe, they see that galaxies tend to cluster in these superclusters, forming intricate networks or cosmic webs. This cosmic structure is not random. It reveals the underlying influence of gravity and the expansion of the universe over billions of years. By studying the size, shape, and distribution of voids and superclusters, scientists gain valuable insights into the distribution of dark matter, the invisible substance that exerts a gravitational pull on galaxies. These observations help refine our models of how the universe evolved from its hot, chaotic early state to the cool, structured cosmos we observe today. The study of these vast structures also offers clues about the future of the universe and how it will continue to evolve. As scientists delve deeper into the complexities of voids and superclusters, they uncover new layers of understanding about the nature of space, time, and the fundamental forces that shape our universe. The quest to understand the universe is a journey that spans both time and space, and at the heart of this pursuit lies the intricate dance between light and the vast cosmic structures that shape its path. By examining how superclusters and voids affect the light from distant galaxies, we unlock deeper insights into the universe's ongoing expansion. These enormous regions, where matter is sparse and spread thin, play a critical role in altering the trajectory of light as it travels through the vastness of space. The gravitational influence of these structures bends and distorts the light, creating subtle variations in how we perceive distant objects. This phenomenon is crucial in our study of the universe's outermost regions, those distant frontiers where light has taken billions of years to journey from its source to our telescopes. Here, in these far-reaching areas, we encounter some of the most profound mysteries of the cosmos, revealing not only the shape and structure of the universe, but also its very history. Cosmic voids and superclusters, the vast and nearly empty spaces alongside dense, galaxy-packed clusters, define some of the largest structures within the universe. Yet their significance extends far beyond their physical presence. These regions guide our investigations into the fundamental nature of the universe, offering essential clues about its large-scale architecture and ultimate destiny. As we piece together this immense cosmic puzzle, we move closer not only to understanding where the universe might end, but also perhaps why it exists in the way that it does. This journey of discovery forces us to confront the deepest questions about existence itself, questions that seem to transcend mere observation and touch on the very essence of space, time, and reality. Integral to these inquiries are the enigmatic black holes, which serve as fascinating gateways into the unknown, challenging our understanding of the observable universe. To grasp the role black holes play in this larger conversation, it's essential to first understand the concept of the observable universe. This is the region of space that we can measure and see, limited by the speed of light and the finite age of the cosmos. Yet, beyond this horizon lies the tantalizing possibility of much more, a vast, perhaps infinite expanse that eludes our direct observation. Black holes are central to this mystery. These regions in space possess an intense gravitational pull, one so powerful that nothing, not even light, can escape once it crosses a boundary known as the event horizon. Once something enters this boundary, it is lost to the observable universe, effectively removed from our view and from the information we can collect. However, this does not imply that the information or the object ceases to exist. Rather, it sparks profound questions about the very nature of space-time itself. What happens to the matter that falls into a black hole? Can it provide insight into the boundaries of our understanding? And perhaps most intriguingly, could black holes serve as portals not just to other realms of our universe, but to other universes altogether? This idea lies at the heart of the multiverse theory, which proposes that our universe might not be unique at all, but rather one of many, each with its own distinct set of physical laws. In such a framework, black holes could function as bridges, connecting separate realities and allowing information to pass between them in ways we can barely begin to imagine. In these speculative scenarios, the conventional rules of physics that we observe in our own universe may not even apply. Moreover, black holes do not merely consume matter. They also play a vital role in the broader cosmic landscape. When they pull in surrounding material, they generate powerful jets of energy that stretch across vast distances. These energetic outbursts suggest that even the aspects of the universe we cannot directly observe may have a profound impact on the cosmos. Black holes, therefore, do not simply represent destructive forces, but rather pivotal features that expand our comprehension of the universe's boundaries and perhaps of the very fabric of reality itself. They are the paradoxes of the cosmos, both enigmatic and essential in our search for meaning in the vast, unknown expanse. Similarly, quasars serve as some of the most powerful and distant beacons in the universe. When we observe the light from a quasar, we are not merely seeing an object in the present moment. We are looking back in time to an era when the universe was still young, only a few billion years after the Big Bang. This time-traveling perspective provides invaluable insight into the early stages of galaxy formation and the development of supermassive black holes, massive structures located at the centers of galaxies, including our own Milky Way. Quasars form when vast amounts of material spiral into these black holes, heating up to extreme temperatures and emitting tremendous amounts of energy in the process. The light we observe from these distant objects has journeyed across the universe for billions of years, offering us a unique window into the conditions that existed in the universe's early days. Despite their faintness when compared to the surrounding stars and galaxies, quasars are often visible even from great distances, making them indispensable tools for understanding the evolution of galaxies over cosmic time. Their light also serves as a crucial probe of the large-scale structure of the universe. As their light passes through vast regions of gas and dust, it carries with it information about the composition and distribution of matter throughout the cosmos. By analyzing this light, astronomers can refine their models of cosmic evolution, gaining deeper insights into the formation and development of galaxies, as well as the distribution of energy and matter across the universe. But quasars are not merely distant, faint objects. They are time capsules, carrying with them vital information about the history of the universe. Through the light they emit, we uncover essential clues about the mechanics of cosmic growth, the behavior of black holes, and the underlying nature of reality itself. Their study remains central to our quest for a more complete understanding of the cosmos, and they continue to be indispensable in our efforts to map the vast, unseen reaches of the universe. Another astonishing phenomenon that plays a crucial role in our understanding of the universe are gamma-ray bursts. These bursts, among the most energetic events in the universe, release massive amounts of energy in the form of gamma rays, often in the span of just a few minutes. The incredible intensity of these bursts challenges our understanding of the universe's structure and behavior. When we observe a gamma-ray burst, it acts as a cosmic beacon, cutting through the vast emptiness of space and illuminating mysteries not just in the vicinity of the burst, but across the cosmos. The origin of these bursts remains one of the greatest enigmas in modern astrophysics. Scientists believe that gamma-ray bursts may result from the collapse of massive stars into black holes or the merger of neutron stars, both scenarios that offer a glimpse into the extreme conditions that govern the life cycles of galaxies, stellar evolution, and the dynamics of dense celestial objects. Studying these bursts provides researchers with invaluable clues about how elements are formed and distributed throughout the universe. This, in turn, helps us to better understand the processes that drive cosmic evolution. Furthermore, gamma-ray bursts can offer insights into the expansion of the universe itself. As the light from these bursts travels across the cosmos, it becomes redshifted, meaning that its wavelength stretches out, shifting toward the red end of the spectrum. This redshift occurs because the universe is expanding, and the farther away an object is, the more its light is stretched. By analyzing the degree of this redshift, scientists can measure the distance to the burst and, importantly, calculate the rate of cosmic expansion. This process provides essential information about the age of the universe and the forces that drive its growth. Thus, through the study of these extraordinary phenomena, black holes, quasars, and gamma-ray bursts, we continue to push the boundaries of our knowledge. Each discovery, each observation brings us one step closer to understanding the vast and intricate universe we inhabit. And as we peer deeper into the cosmos, we uncover not only the mechanics of the universe's evolution, but also the profound questions that drive our quest for understanding, questions that challenge the very limits of human imagination. Gamma-ray bursts present an intriguing, albeit puzzling, aspect of cosmic phenomena. These bursts, as brief as they may be, release an astonishing amount of energy, far surpassing anything humans can fathom. They occur when massive stars collapse or when two neutron stars or black holes collide, sending shockwaves throughout the fabric of space itself. This immense energy released by the bursts impacts the surrounding space in profound ways, potentially sparking the formation of new stars. At the same time, they influence the evolution of existing ones, making gamma-ray bursts not just fleeting explosions of light, but potent agents of cosmic change. By studying the aftermath of these bursts, scientists are unraveling the story of how galaxies grow and evolve, shedding light on the deep forces that shape the universe. Moreover, gamma-ray bursts serve as markers in the vast landscape of the cosmos. They hold clues to some of the most elusive mysteries in astrophysics, such as their origins and their role in the universe's expansion. With each burst we observe, we gain a glimpse into the violent and dynamic processes that shape the universe. These events give us a unique window into the very heart of cosmic evolution, allowing us to better understand how matter, energy, and gravity interact on the grandest scales. In this sense, gamma-ray bursts aren't just phenomena to be studied. They are cosmic signposts, guiding us through the narrative of the universe's creation and growth. In a similar vein, gravitational waves offer a completely new way of observing the universe. These ripples in the fabric of space-time, created by some of the most energetic events, carry crucial information about their origins. Events such as the collision of black holes or neutron stars send these waves traveling through space, providing a new auditory dimension to our cosmic understanding. The analogy of tossing a stone into a still pond perfectly captures how gravitational waves propagate. As the stone creates ripples on the water's surface, these waves ripple through space-time, allowing us to hear the cosmic events that generated them. This new method of observing the universe is an incredible leap forward in our ability to understand the most energetic and enigmatic phenomena in existence. When two massive objects, such as black holes or neutron stars, orbit one another, they disturb the surrounding space-time. As they spiral inward, getting closer and closer, they send out bursts of gravitational waves. These waves can travel across vast distances, unaffected by the intervening material in space, unlike light, which can be blocked or distorted by cosmic dust. As a result, gravitational waves offer us an unobstructed view of the universe, revealing the hidden dynamics of phenomena that are otherwise invisible. Detecting these waves gives scientists a wealth of information, from the masses and velocities of the objects involved to their distance from Earth. With these details, astronomers can reconstruct the events that generated these waves, painting a vivid picture of the forces at play in some of the most extreme environments in the cosmos. Furthermore, gravitational waves complement traditional methods of astronomical observation, such as the study of light. While telescopes capture stunning images of distant stars and galaxies, their view is often hindered by cosmic dust, or they can only reveal certain wavelengths of light. Gravitational waves, on the other hand, travel through space without distortion, unveiling aspects of the universe that would otherwise remain hidden. This dual approach, combining both light-based observations and gravitational wave detection, offers a fuller, more nuanced understanding of the universe's complexities. It enhances our grasp of how stars are born, how galaxies evolve, and how gravity itself shapes the cosmos on the largest scales. Dark matter, an invisible yet essential component of the universe, plays a pivotal role in shaping the cosmos. Imagine the universe as a massive, intricate tapestry, where the majority of the material that holds it all together is invisible to us. We cannot directly see dark matter, yet it exerts a profound gravitational influence on the matter we can observe. About a quarter of the universe is thought to be composed of dark matter, a substance that does not emit, absorb, or reflect light. Yet, its presence is inferred from its gravitational effects on visible matter, such as galaxies and galaxy clusters. Without dark matter, the motion of galaxies would be chaotic and unpredictable. Galaxies rotate as though there is far more mass present than we can observe. This unseen force shapes the universe in ways that scientists are still working to fully comprehend. Astronomers map the universe's dark matter through gravitational lensing, a phenomenon where the gravitational pull of massive galaxy clusters bends light from more distant objects. This stretching and distortion of light allow researchers to trace the location and concentration of dark matter, offering glimpses into the unseen regions of the cosmos. These maps provide a more complete picture of the universe's structure, revealing how dark matter influences the formation and clustering of galaxies over billions of years. Without dark matter, the very structure of the universe would be vastly different, and our understanding of cosmic evolution would remain incomplete. Moreover, advancements in computer simulations have dramatically transformed our understanding of the universe. These powerful simulations allow scientists to visualize the universe's vast and complex structures in ways that were once thought impossible. It's like trying to map a landscape that no one has ever physically visited. Yet, through computation, researchers can create detailed models of how galaxies, dark matter, and cosmic structures evolve over billions of years. Using sophisticated computing technology, scientists simulate the behavior of these cosmic entities based on the known laws of physics, such as gravity and the dynamics of gases, to recreate the environment of the early universe. The results are stunning visualizations, offering a dynamic and ever-evolving picture of how galaxies formed, how they clustered, and how the vast cosmic web of dark matter took shape across the universe. These simulations allow researchers to vary different parameters, such as the amount of dark matter or the rate of galaxy formation, to explore a wide range of scenarios. This enables them to gain insights into the distribution of galaxies and the large-scale structures that dominate the universe, such as galaxy clusters and the interconnected cosmic web. By mimicking the complex dynamics of the universe, simulations provide valuable information about the nature of dark matter, the formation of galaxies, and the forces that drive cosmic evolution. With these advanced tools, our understanding of the universe is more expansive than ever before, unlocking new ways to visualize and explore the grand tapestry of the cosmos. Moreover, as data from telescopes continue to improve and an ever-growing wealth of observational information becomes available, simulations of the universe can be refined to an even greater degree. These simulations are not merely theoretical exercises, they serve as a crucial testing ground for scientific theories. By comparing the simulated results with actual observations, scientists are able to validate or challenge their models. This iterative process does more than confirm what we already know. It often unveils new phenomena that were previously unconsidered or unknown. In this way, these computer-generated views of the universe's farthest reaches are far more than artistic representations. They are foundational tools for modern astrophysics, offering a clearer, more precise understanding of the universe's structure, expansion, and the elusive substances that constitute it, like dark energy. Through these sophisticated simulations, we gain an increasingly deeper appreciation for the cosmos. The sheer scale of the universe, the complexity of its systems, and the myriad mysteries that remain just beyond our grasp come into sharper focus. As technology advances, artificial intelligence, AI, and machine learning are revolutionizing our approach to cosmic research, processing vast amounts of data at an unprecedented rate. These technologies are unveiling patterns and insights that would be nearly impossible for human analysts to detect, allowing for breakthroughs in our understanding of the universe. Space telescopes, for instance, constantly collect an overwhelming amount of data about celestial objects, phenomena, and the universe's ongoing expansion. In this context, machine learning algorithms act as powerful tools to sift through this data, categorizing objects, identifying anomalies, and predicting behaviors based on historical trends. One of the most intriguing applications of this technology lies in the search for exoplanets. By analyzing the light emitted from distant stars, machine learning algorithms can detect tiny dimming patterns that occur when a planet crosses in front of its star. These subtle variations in light may go unnoticed by human eyes, but AI-driven systems can identify them with remarkable precision, accelerating the discovery of new exoplanets and speeding up the process of characterizing these distant worlds. Machine learning also plays a pivotal role in the study of the cosmic microwave background, CMB, which is the faint afterglow of the Big Bang. By organizing and interpreting this data, AI systems help trace the early moments of the universe, offering crucial insights into its overall structure and dynamics. Similarly, in the realm of gravitational wave astronomy, AI-driven algorithms trained on previous wave signals can detect faint ripples in spacetime caused by cosmic events, such as the collision of black holes. This ability allows scientists to observe phenomena that were once completely undetectable, further enhancing our understanding of the cosmos and opening the door to new discoveries. Furthermore, AI integration into space missions is proving invaluable in navigating spacecraft and making real-time decisions. As missions venture further into space, unexpected challenges often arise, requiring quick and adaptive responses. AI enables spacecraft to adjust their course or even make autonomous decisions without waiting for instructions from Earth. This level of adaptability is crucial for the success of future space exploration, ensuring that missions can continue smoothly, even in the face of unforeseen obstacles. Together, these advancements in artificial intelligence and machine learning are transforming the landscape of space exploration. By turning vast amounts of raw data into actionable scientific insights, these technologies help shape our understanding of the universe and will undoubtedly guide us in our quest to uncover its deepest secrets. Looking ahead, future space missions promise to expand our knowledge in ways we have only begun to imagine. As we continue to push the boundaries of what we can observe, new technologies will allow us to explore deeper into the cosmos beyond the limits of our current observational capabilities. The observable universe is defined by the distance that light has traveled since the Big Bang, but as our observational technology improves, we are able to peer further back in time and space. Innovations in telescope design, materials, and imaging technology are opening new possibilities for detecting fainter and more distant objects in the cosmos. A key advancement in this field could involve the deployment of space telescopes designed to observe in different wavelengths, such as infrared or even radio frequencies. These telescopes have the potential to peer through cosmic dust clouds, unveiling celestial phenomena that would otherwise be hidden from view. One of the most exciting prospects of such missions is the ability to capture images of the earliest galaxies that formed after the Big Bang. By studying these ancient structures, we can gain a better understanding of the processes that shaped the universe and the conditions that led to the formation of the first stars and galaxies. Moreover, missions equipped with advanced spectrometers can analyze the light emitted by distant objects, revealing their chemical compositions, temperatures, velocities, and even their rates of rotation. This wealth of data will help scientists piece together the story of how these objects formed and evolved over billions of years. Another area ripe for exploration is the study of dark matter and dark energy, two of the most mysterious and enigmatic components of the universe. These substances make up the majority of the cosmos, yet we still know very little about them. Dark matter, which is thought to interact with normal matter through gravity, remains invisible to our telescopes, and dark energy, responsible for the universe's accelerated expansion, is an even greater enigma. Missions aimed at mapping the distribution of dark matter across vast cosmic scales could offer vital clues to its role in the formation of galaxies and large-scale structures. Similarly, a deeper understanding of dark energy could reveal more about the fate of the universe itself, offering insights into whether the universe will continue expanding indefinitely, collapse, or eventually reach a state of equilibrium. Beyond the immediate boundaries of the observable universe, the potential to explore what lies beyond the so-called cosmic horizon is becoming more tangible. Gravitational wave astronomy, for instance, could provide a new window into this distant frontier. Gravitational waves are ripples in space-time caused by some of the most violent and energetic events in the universe, such as the collision of black holes or neutron stars. These waves carry valuable information about regions of the universe that are otherwise inaccessible to traditional telescopes. As technology improves, we may be able to detect more of these waves, unveiling new layers of cosmic history and expanding our understanding of the universe's vastness. In addition to these advancements in observational technology, collaboration between space agencies and private enterprises is accelerating the pace of exploration. As new players enter the field, ambitious missions are being proposed to explore interstellar or even intergalactic space. These missions, which once seemed like the stuff of science fiction, are slowly becoming a reality. By pushing the boundaries of our observational capacity, each mission brings us closer to understanding the fundamental laws that govern the universe, allowing us to answer questions that challenge the very fabric of existence itself. As we venture deeper into space, a host of cutting-edge technologies promises to further expand our reach. One of the most exciting developments in this area is the potential for advanced propulsion systems. Traditional rocket engines, which rely on chemical reactions for thrust, have served us well but are inherently limited by the vast distances between stars and planets. Emerging technologies such as ion propulsion and laser sail technology offer a glimpse of what the future may hold. Ion propulsion systems work by accelerating ions to generate thrust, making long-distance journeys possible without the need for large quantities of propellant. Laser sail technology, meanwhile, could use powerful beams of light to propel spacecraft at incredible speeds, potentially enabling us to reach distant star systems in a fraction of the time it would take with conventional rockets. Alongside these advancements in propulsion, the development of robotics and autonomous systems is revolutionizing space exploration. Robots equipped with AI can perform complex tasks in environments that are too dangerous for humans. For example, rovers currently operate on Mars, gathering valuable data about the planet's surface, but future models could be designed to venture into more hazardous regions, collecting data that would otherwise be inaccessible. Moreover, the ability to manufacture tools and spare parts in space through 3D printing is a game changer. This technology has the potential to drastically reduce the costs of space missions by enabling astronauts to produce what they need on demand, rather than relying on expensive resupply missions from Earth. As we look to the future of space exploration, these technologies will not only make our missions more efficient and sustainable, but also open up new possibilities for discovery. With each new advancement, we move closer to answering the most fundamental questions about the universe and our place within it, offering the hope that one day we may uncover the full extent of the cosmos and the mysteries it holds. Furthermore, recent advancements in the field of material science are playing a crucial role in shaping the future of space exploration. Scientists are developing new materials capable of withstanding the extreme conditions of space, such as intense radiation and fluctuating temperatures. These innovations are paving the way for spacecraft that can endure the harsh realities of interstellar travel, providing crucial protection for astronauts and equipment. With these breakthroughs, missions that once seemed unattainable may soon become a reality. The integration of these advanced materials promises not only safer voyages, but also the possibility of more frequent and longer missions into the farthest reaches of space. In parallel, communication technologies are experiencing rapid progress, which is equally vital for the continued expansion of space exploration. One particularly exciting development is quantum communication. This technology, still in its early stages, holds the potential to revolutionize the way information is transmitted across vast distances. Unlike traditional communication methods, which are limited by the speed of light, quantum communication could allow for near instantaneous transmission of data between Earth and distant space missions. This would drastically reduce the delays that have long hindered real-time communication and decision-making. With faster and more reliable communication systems, astronauts would be able to make more informed choices in the midst of their missions, leading to more effective collaboration and quicker responses to unexpected challenges. Collectively, these emerging technologies, materials science, and advanced communications represent a thrilling frontier in space exploration, offering unprecedented opportunities to push the boundaries of human knowledge and capability. As new discoveries are made and as our technological abilities grow, our understanding of the universe will expand in ways we can only begin to imagine. Equally important is the collaborative spirit that unites the world's space agencies. This international cooperation is essential for tackling the complex challenges that space exploration presents. Just as a telescope brings distant objects into clearer focus, collaboration between countries broadens our perspective of the cosmos, allowing us to collectively tackle problems too complex for any single nation or organization. Agencies such as NASA, the European Space Agency, ESA, and others share not only financial resources, but also valuable expertise, technology, and scientific knowledge. This shared pool of resources and talents has been instrumental in advancing humanity's space exploration efforts. One of the most significant outcomes of such international partnerships is the ability to launch larger and more ambitious missions. Take, for example, the Hubble Space Telescope. a collaborative project involving NASA and the European Space Agency, which has fundamentally transformed our understanding of the universe through its breathtaking imagery and invaluable data. By pooling their resources and combining their technological prowess, space agencies are able to launch missions that extend further into space and gather more comprehensive data. A powerful example of this can be seen in the sharing of satellite data, which allows countries to build a more complete and accurate picture of the cosmos. Together, they have been able to study phenomena such as the distribution of galaxies, the behavior of dark matter, and the very evolution of the universe itself. Each space agency brings its own unique set of instruments to the table, allowing for a diverse range of observations. This diversity in observational tools helps scientists explore celestial bodies in different wavelengths of light, revealing details that might otherwise remain hidden. The combined data collected from multiple agencies offers a more nuanced understanding of the universe, unveiling secrets that were previously beyond our reach. Additionally, these collaborations help foster a sense of unity among the global scientific community. By sharing knowledge and working together, scientists from different corners of the world contribute their unique perspectives, driving innovation and advancing research in new and unexpected directions. This exchange of ideas accelerates discoveries, enabling the faster development of new technologies that will be crucial for future missions. The collaboration between space agencies not only leads to more efficient exploration, but also strengthens the bonds between nations, creating a sense of shared purpose in the pursuit of knowledge. Looking beyond the technical benefits, international collaboration also has profound cultural implications. The ability to unite scientists from diverse backgrounds encourages a broader, more inclusive approach to problem solving. This diversity enhances creativity and enriches the scientific process, ensuring that a wider range of ideas is considered. In this way, space exploration becomes not just a technological endeavor, but a cultural one, where different cultures contribute their wisdom and expertise to uncover the mysteries of the universe. The sense of global unity in space exploration is a testament to the power of cooperation, showing that together, humanity can achieve great things. As we stand on the edge of space, the mysteries of the universe beckon us to explore further, beyond our current limits. The observable universe, as vast as it may seem, is only a fraction of what lies beyond. Defined by the farthest light that has had time to reach us since the beginning of cosmic expansion, the observable universe provides a glimpse into the earliest moments of cosmic history. Beyond this boundary, space behaves in ways that continue to astonish and challenge our understanding. The universe is not a static entity, it is constantly expanding. Regions of space beyond the observable horizon are moving away from us at extraordinary speeds. Some of these areas are receding so rapidly that their light may never reach us, potentially making them permanently out of our observational reach. This presents a fascinating paradox. While we can only study the universe within the observable limits, the true scope of the cosmos is far greater, potentially extending into regions that are forever beyond our understanding. As we look further into the depths of space, we encounter the concept of cosmic inflation. This was a period during the universe's early history when it expanded at an unprecedented rate. It suggests the possibility that there are regions of space vastly different from our own, with unique properties and possibly even different physical laws. These regions could harbor entirely different cosmic phenomena, galaxies formed under different conditions, or perhaps even alternate realities governed by different rules. The idea of multiple universes or multiverses remains a topic of intense speculation among scientists, and the further we look, the more questions arise. At the very edges of the observable universe, we confront the limits of our knowledge. The closer we get to these boundaries, the more we must confront the possibility that the universe might be infinite. What lies beyond the observable universe? Is it simply an unending expanse of more galaxies, or could it be something far stranger, leading into entirely different realms? The answers to these questions are tantalizingly out of reach, but they continue to drive our quest for knowledge. As our technology advances, we move ever closer to answering these profound questions. The edges of the observable universe are not just physical boundaries. They represent the limits of human understanding, constantly pushing us to ask deeper and more fundamental questions. Each discovery brings us closer to unraveling the mysteries of space, and with it, a greater understanding of our place in the cosmos. To grasp the complexity of space-time curvature, it is useful to imagine the universe as a vast, interconnected fabric, where space and time are woven together. This fabric is not flat, but is instead shaped and distorted by the presence of massive objects, such as stars, planets, and black holes. The more massive an object, the greater its ability to bend the fabric of space-time around it. This curvature is the essence of gravity, which, rather than acting as a simple force pulling objects together, can be more accurately understood as the result of objects following curved paths within this distorted fabric. This concept of space-time curvature has profound implications for our understanding of the universe's boundaries. In regions where the curvature of space-time is particularly strong, such as near black holes, the paths of objects become drastically altered. Even light, which normally travels in a straight line, is bent by the curvature, leading to phenomena such as gravitational lensing, where light from distant stars is warped by the gravitational pull of massive objects. One of the most fascinating aspects of this curvature is the event horizon of a black hole, the boundary beyond which no information or matter can escape. Once something crosses this threshold, it becomes invisible to us, beyond the reach of any observation or understanding. The event horizon marks a point of no return, a place where the fabric of space-time becomes so distorted that not even light can escape its grasp. This mysterious boundary represents the limits of our observational capabilities, reminding us of how much there is still to learn about the universe and the forces that govern it. Furthermore, the curvature of space-time plays a significant role in the ongoing expansion of the universe. It's not as if galaxies are simply drifting apart into the emptiness of space. Instead, they are moving along the curves of an ever-expanding fabric of space-time itself. This movement suggests that the universe might not be infinite as we often imagine it, but could rather possess a unique shape and boundaries that are defined by its contents. Think of it like the surface of a balloon, one that continuously expands without ever truly becoming infinite. This analogy helps conceptualize how the universe may be finite, despite its vastness. Understanding the curvature of space-time helps scientists develop theories regarding the overall structure of the universe and its potential fate. This exploration not only shapes our knowledge of what lies beyond the edges of our observable universe, but also reveals how all the cosmic components are interconnected, providing a deeper insight into the grand design of existence. As we look further into the far reaches of the universe, we encounter the concept of time dilation, which fundamentally alters our perception of time itself. Time behaves differently in various parts of the universe, especially in regions governed by the immense gravitational forces of massive cosmic structures like black holes or galaxy clusters. According to Einstein's theory of relativity, time does not flow uniformly. Rather, it stretches and compresses depending on the strength of the gravitational fields. At the universe's outer edges, where gravity is not as intense as in the immediate vicinity of a black hole, you might still experience noticeable differences in the passage of time when compared to someone far away in a completely different gravitational environment. For example, if you were to embark on a journey to the farthest reaches of space where gravity is weaker, time would pass more quickly for you compared to someone who remains on Earth. Upon returning, you would discover that years had passed for those left behind, while only a short period of time had elapsed for you. Moreover, as the universe continues to expand, light from distant galaxies undergoes a shift in frequency due to this expansion, a phenomenon known as redshift. This further enriches our understanding of time. Not only is time influenced by gravity, but the very fabric of space is also stretching, altering the distances between objects in relation to the flow of time. The implications of such time dilation have profound consequences for long-term space travel and our understanding of the universe's history. It raises critical questions about the synchronization of events across vast cosmic distances and how time can shape our perception of existence in ways that challenge our fundamental understanding. Time dilation at the universe's farthest reaches demonstrates how inextricably linked space and time are. This poses a philosophical dilemma about our place within the cosmos, prompting us to reconsider how we measure the passage of time from both human and cosmic perspectives. The observable universe is often likened to a bubble within a much larger, incomprehensible cosmic domain. The space we can measure and observe is limited by how far light has traveled since the beginning of time. Imagine a balloon expanding. The surface of the balloon grows. In this analogy, the observable universe is the surface, while what lies beyond remains a mystery. This uncharted territory could contain additional spatial dimensions beyond our comprehension. While we experience the universe in 3 dimensions, length, width, and height, it's possible that additional dimensions exist outside of our observational limits, offering the potential for interactions or forces beyond our current understanding. To put this in perspective, consider how a 2-dimensional being would perceive our 3-dimensional world. Their perception would be confined to their 2-dimensional space, just as our understanding of reality may be confined to the 3 dimensions we can observe. What lies beyond the observable universe might operate under entirely different physical laws, creating realms of existence that challenge everything we know. These dimensions could host behaviors of space and time that differ drastically from what we are accustomed to. The complexities of such realms could unlock phenomena and interactions that radically change our understanding of reality. If only we could peer beyond the boundaries of our observational bubble, we might discover an entirely new fabric of space, time, and existence itself. In the known universe, time is not a fixed constant. Its flow varies depending on the influence of cosmic factors. In regions where gravity is particularly strong, such as near a black hole or a neutron star, time is perceived differently. This is due to the effect known as gravitational time dilation. Imagine 2 clocks, one on Earth, the other near a black hole. From a distance, the clock near the black hole would appear to tick slowly. However, for someone near the black hole, their perception of time remains normal. Yet, from the perspective of an observer far away, it would seem as though time is stretching out in a cosmic dance, stretching into eternity. The movement of objects through space at immense speeds also alters the perception of time. According to Einstein's theory of relativity, velocity has a similar effect on time as gravity. Picture 2 twins. One remains on Earth, while the other travels through the galaxy at speeds approaching that of light. Upon returning, the traveling twin would find themselves younger than their sibling. This phenomenon, known as time dilation, demonstrates how speed, much like gravity, can warp the fabric of time itself. In more mysterious regions of the universe, particularly near the event horizon of a black hole, the forces of gravity are so immense that time may appear to freeze. As an object approaches the boundary known as the point of no return, an external observer would witness the clock of the traveler near the black hole ticking slower and slower, it seemingly frozen in time. It would seem as though the traveler could never escape the black hole's grip, trapped forever in a state where time behaves entirely differently. Combining these concepts, the stretching of time due to gravity, velocity, and cosmic structures, unveils a universe far stranger than we ever imagined. The variations in time experienced across different regions challenge our understanding of the very nature of reality. They reveal a universe in which time is not a constant, but a fluid and ever-changing dimension influenced by the forces surrounding it. These concepts do not just challenge our scientific models, they also force us to confront deeper philosophical questions about the nature of existence and our place within the vast cosmos. At the very edges of the universe, subatomic particles exhibit behaviors that are influenced by the extreme conditions of space and the fundamental laws of physics. The universe is not a static, unchanging place. It is a dynamic, ever-shifting environment, shaped by gravitational forces, electromagnetic interactions, and other cosmic phenomena. In the farthest reaches of the universe, where cosmic expansion takes place, particles interact in ways that are still not fully understood. These particles, which we traditionally think of as discrete entities, may actually be interconnected, existing as part of a larger field that continuously influences their behavior. The farthest corners of the universe, where the fabric of space itself stretches and distorts, offer a glimpse into the true nature of the cosmos, one where the laws of physics break down, where the behavior of matter and energy becomes unpredictable, and where the boundaries of space and time are continually redefined. This reality challenges everything we thought we knew about the universe and forces us to reconsider the very fabric of existence itself. As we continue to explore these frontiers, we begin to understand that the universe is not just an environment we inhabit. It is an ever-evolving, living entity, full of mysteries waiting to be unraveled. As we approach the outer edges of the observable universe, quantum fluctuations begin to play a more significant role. These fluctuations are brief, seemingly random shifts in energy that can give rise to pairs of particles and antiparticles. It's almost as though the very fabric of space, that vast vacuum that we once considered empty, is far from being still. Instead, it is constantly buzzing with activity, a ceaseless hum of creation and annihilation that occurs on the most microscopic scales. In regions where the space is less stable or more chaotic, this dance of particles can lead to a rich and complex tapestry of interactions, ones that would rarely manifest in more well-established, quieter parts of the universe. This concept of boundary areas extends further into the idea of cosmic horizons. These are regions beyond which no information can reach an observer, making them effectively unreachable, not only physically, but also in terms of influence or communication. In such zones, particles may still exert subtle, intricate influences on their surroundings, yet these interactions remain hidden from us. For example, light emitted by particles in these far-flung regions may never reach us, instead moving toward these unreachable areas, shrouding our view of the universe. It is as if there is a cosmic veil, one that obscures vast swaths of the universe from our sight, further deepening the mystery of what lies beyond. As we venture deeper into the behavior of subatomic particles at such colossal scales, we find ourselves unraveling a ceaseless ballet of forces and energies, a constant interplay where uncertainty reigns. The particles themselves, their motions, their behaviors defy the neat equations and predictable patterns that we tend to rely on in classical physics. In these realms, the very foundation of our understanding of the universe begins to tremble, sparking the creation of new theories and ideas. The more we study, the more we realize that the rules of physics bend and twist in ways that seem counterintuitive, revealing glimpses into a reality far more complex than we ever anticipated. Neutrinos, for instance, are among the most enigmatic particles we have encountered. These nearly massless, incredibly tiny particles travel at speeds approaching that of light, and they are produced in abundance during some of the most cataclysmic events in the universe, such as nuclear fusion within stars, the explosive violence of supernova, and even in the cosmic collisions caused by cosmic rays interacting with the Earth's atmosphere. Their most defining characteristic, however, is their ability to pass through matter with hardly any interaction. It is said that neutrinos could travel through a light year of lead without being deflected or absorbed. This elusive quality makes neutrinos a unique and powerful tool for scientists. They offer an entirely different kind of observational capability, one that doesn't rely on traditional forms of radiation or light. As neutrinos stream across the cosmos, they carry with them valuable information about their origins, information about the violent, energetic processes that produce them. By detecting and analyzing neutrinos, scientists can peer into the heart of phenomena that would otherwise remain hidden, such as the inner workings of stars or the chaotic dynamics within supernova explosions. Moreover, neutrinos offer us a rare window into the early universe. Since they interact so weakly with matter, they can travel vast distances, allowing them to carry information about the conditions that existed shortly after the Big Bang. This opens up profound possibilities for understanding the very forces that shaped our universe in its infancy. Neutrinos could hold the key to answering some of the most fundamental questions in cosmology. What is dark matter? What is the true nature of the universe's expansion? These particles, in their quiet journey across the cosmos, are like messengers, providing us with insights from distant and violent corners of the universe, helping to reshape our understanding of the cosmos. The concept of antimatter, the mirror image of ordinary matter, brings even more complexity into the equation. Antimatter consists of particles that have the same mass as their matter counterparts, but with opposite charges. On Earth, antimatter is created in particle accelerators, where it exists briefly before it annihilates when it comes into contact with matter, releasing vast amounts of energy in the form of light and heat. Yet, beyond the boundaries of the observable universe, the nature of antimatter becomes even more fascinating. It's hypothesized that regions far beyond our observational reach may harbor vast amounts of antimatter, existing in clusters that we cannot yet detect simply because the light from these regions hasn't had the time to reach us. In these hidden areas, antimatter might follow entirely different trajectories and interactions compared to matter. Perhaps entire star systems made entirely of antimatter exist in these unseen corners of the universe, forming their own cosmic ecosystems. The implications of antimatter existing in these distant, unseen regions are mind-boggling. If such antimatter is affected differently by gravity and radiation than matter, it could lead to the formation of structures and patterns that defy our current understanding. Yet, despite the potential differences, the fundamental laws of physics would likely remain intact. Still, the very idea of antimatter residing in these remote areas of the universe challenges our current cosmological models, offering tantalizing hints about the nature of dark matter and the very fabric of reality itself. As our technology advances and our observational tools become more sophisticated, who knows what revelations may await us? What insights might we gain from these dark expanses of the universe, where antimatter could potentially reside? The search for answers is one that continues to drive us to the farthest reaches of space and knowledge. Cosmic rays, high-energy particles that constantly bombard the Earth, offer yet another fascinating avenue of exploration. These cosmic messengers carry energies that are far beyond anything we can produce with our own particle accelerators. When cosmic rays collide with atoms in Earth's atmosphere, they generate cascades of secondary particles and radiation, which can be detected by specialized instruments. By studying these cosmic rays, scientists can trace their origins back to some of the most powerful and explosive events in the universe, such as supernovae or the active nuclei of distant galaxies. The energies carried by these particles are of a magnitude so high that they surpass even the most energetic man-made collisions. As such, cosmic rays serve as a unique means of exploring regions of space that would otherwise remain beyond our grasp. They offer a window into the composition and structure of distant celestial bodies, be they stars, galaxies, or other cosmic phenomena, providing us with insights into their chemical makeup and internal dynamics. In a sense, cosmic rays are a direct connection to the most energetic, violent processes occurring in the universe, allowing us to study the distant reaches of space in a way that would be otherwise impossible. Furthermore, cosmic rays are key players in advancing our understanding of cosmic magnetic fields. These high-energy particles, charged by nature, traverse vast distances through the universe. As they travel, they encounter and interact with magnetic forces that bend and distort their paths. By analyzing the intricate patterns of energy levels and the timing of their arrival on Earth, scientists can piece together valuable information about the magnetic environments these cosmic rays have passed through. This process aids in mapping the structure and behavior of the invisible magnetic fields that exist between celestial bodies, offering insights into the forces that shape the cosmos at large. In essence, cosmic rays act as messengers from the furthest reaches of the universe, enhancing our knowledge of the mysteries that lie beyond our sight. The study of these particles not only helps scientists explore various cosmic phenomena, but also tests the fundamental laws of physics in settings that are radically different from conditions found on Earth. Through their journeys, these particles provide a lens through which we can observe the universe in ways that were previously unthinkable. They open up new avenues for understanding the events that shaped our universe's evolution and offer clues about the fundamental forces that govern it. Exotic particles, in particular, play an integral role in this quest for knowledge. Exotic particles are some of the most intriguing contributors to our grasp of the universe's complex nature, especially when theorizing about its outer limits and unexplored edges. These particles often exhibit properties that are far from the norm, exhibiting behavior and characteristics that diverge significantly from the more familiar protons, neutrons, and electrons, which constitute ordinary matter. Some exotic particles might possess unusual charges or display mass properties that cause them to interact with the fundamental forces of nature in ways we are only beginning to understand. One of the most fascinating aspects of these exotic particles is how they influence matter and energy at extreme scales and conditions, such as those found near the edges of the cosmos or within vast, unexplored regions like the mysterious halos of dark matter. Their existence supports theories that suggest the universe may be structured in ways that are not immediately observable, hinting at the presence of phenomena that exist beyond the limits of current observational technology. When theorizing about the universe's edges, exotic particles become potential agents of change, helping scientists explain some of the more perplexing phenomena that defy our understanding, such as the force behind the accelerated expansion of the universe. This mysterious force, known as dark energy, may have an essential connection to the behavior of these exotic particles. By studying the interactions of such particles at the far reaches of space, researchers hope to uncover the secrets behind the formation and evolution of galaxies, as well as gain insight into the large-scale structure of the universe itself. Moreover, the study of exotic particles introduces revolutionary concepts that stretch our imagination, such as the idea of multiple dimensions existing beyond our familiar three-dimensional space. These theories propose that the universe might hold hidden aspects, realms, or properties just waiting to be uncovered at the farthest fringes of space. This perspective compels scientists to explore models where exotic particles might be manifesting in ways that are currently undetectable, suggesting that the universe's outermost edges are not barren, uninhabited voids, but rather regions brimming with activity governed by physics that humanity is only beginning to comprehend. Thus, these exotic particles provide essential puzzle pieces in our ongoing quest to understand the universe's boundaries. By acting as cosmic connectors, they help us link together various phenomena across the universe, allowing us to speculate not only about what might lie beyond our observable universe, but also about what transformative changes could be occurring just beyond our current reach. Cosmic evolution, as a whole, tells the grand narrative of how the universe has unfolded over billions of years, ultimately giving rise to the observable cosmos we see today. This story begins with the Big Bang, a monumental explosion that ignited the expansion of space and time around 14 billion years ago. In the immediate aftermath, the universe was an incredibly hot and dense environment, filled with elementary particles. As it rapidly expanded, it began to cool, and these particles started to combine into the simplest of atoms, hydrogen and helium. Over time, these gas clouds began to condense and coalesce under the relentless force of gravity, forming the first stars and galaxies. Imagine the universe as a vast canvas, where a cosmic artist methodically crafts complex structures over time. Stars, through nuclear fusion, generated increasingly heavier elements within their cores during their lifetimes, enriching the surrounding hydrogen and helium clouds with heavier elements. When these massive stars reached the end of their life cycles, they exploded in a magnificent display of a supernova, scattering these heavier elements into space and seeding the formation of new stars, planets, and other cosmic bodies. This cyclical process of stellar birth and death, known as stellar evolution, has been pivotal in shaping the diverse array of elements and structures found throughout the universe today. Over billions of years, galaxies evolved, collided, and merged, giving rise to even larger cosmic structures known as galaxy clusters and superclusters. This dynamic interplay of gravitational forces ultimately formed the cosmic web, a vast, interconnected arrangement of filaments and voids that governs the distribution of galaxies we observe today. The evolution of galaxies themselves also had a profound impact on their physical characteristics, their shapes, sizes, and the types of stars they harbor. Our observable universe is a complex mosaic of countless galaxies, each with its own unique story of formation and change. Even remnants of the early universe persist in the form of cosmic microwave background radiation, a faint, almost imperceptible glow that fills the universe and serves as a snapshot of the cosmos when it was just a few 100,000 years old. This faint afterglow offers a treasure trove of information, allowing scientists to probe the conditions of the early universe, providing crucial insights into the cosmic environment that existed shortly after the Big Bang. Moreover, the universe's expansion continues to this day, driven by enigmatic forces like dark energy. This expansion, which started during the Big Bang, shows no signs of slowing down. In fact, recent observations suggest that not only is the universe still expanding, but the rate at which it is expanding is also accelerating. This startling revelation emerged from the study of distant supernovae, whose light revealed that galaxies are moving apart faster now than they were in the past. One prominent explanation for this accelerating expansion is the mysterious dark energy, a force that permeates space and works against the force of gravity. To visualize this, imagine blowing up a balloon. While the balloon expands, the points marked on its surface move away from each other at an increasing rate. Similarly, as the universe expands, galaxies are moving further apart from one another at an accelerating pace. Looking into the future, this accelerated expansion is expected to continue. If dark energy remains constant, galaxies will continue to drift further apart over billions of years, eventually becoming so distant from each other that they will no longer be visible to one another. This could lead to a scenario known as the Big Freeze, where galaxies become isolated and the universe becomes an increasingly empty and dark place. In this far distant future, stars will have exhausted their nuclear fuel, leaving behind cold, dark remnants like black holes and neutron stars. While this scenario paints a rather bleak picture of the universe's future, it is important to remember that this is a process that will unfold over incomprehensibly long timescales. Yet it serves as a poignant reminder of the universe's inevitable transformation. As we continue to study cosmic evolution, we gain a deeper understanding not only of where we are today, but also of how we arrived here, and, perhaps most importantly, how the universe might evolve in the far future. However, alternative theories exist that suggest different outcomes for the universe's future, offering perspectives that challenge the prevailing understanding of its continued expansion. One such theory proposes that the nature of dark energy, which is believed to be responsible for the accelerated expansion of the universe, could change over time. If dark energy were to weaken or behave differently than expected, it might slow down the rate of expansion, or perhaps even reverse it entirely. This could lead to a scenario known as the Big Crunch, where the universe collapses in on itself, reversing the process of cosmic expansion that began with the Big Bang. While this perspective is less favored by current observations, it continues to fuel spirited discussions in the field of theoretical astrophysics. These debates illustrate the uncertainty that still surrounds our understanding of the universe's ultimate fate. At present, scientists possess a reasonably strong grasp of the current trends in the universe's expansion, yet the future remains a vast, uncharted frontier full of possibilities. Every new discovery in cosmology adds a layer of depth to our understanding of the complex processes governing the cosmos. With each advancement, we are reminded of the universe's vastness and its ceaseless dynamism. The continuous unfolding of its mysteries challenges us to rethink everything we know, pushing the boundaries of what we thought was possible. To explore these mysteries, scientists employ a combination of advanced simulations and theoretical models that attempt to recreate the conditions of the universe just after the Big Bang. Imagine a time just moments after the universe began, an incredibly hot, dense soup of particles. It was a state of chaos where the fundamental forces and components of the universe, including gravity, electromagnetism, and the strong and weak nuclear forces, were still taking shape. In order to understand how this primordial state evolved into the vast cosmos we observe today, scientists use powerful supercomputers to simulate these conditions. These simulations start with mathematical models that describe how matter interacts under extreme conditions, influenced by the fundamental forces at play. Theories of inflation, suggesting that space expanded exponentially in the earliest moments of the universe, are a key component of these models. This rapid expansion caused tiny quantum fluctuations to grow, eventually forming the large-scale structures we see today. By breaking space into a grid, researchers can track the movements of galaxies, dark matter, and gas over vast stretches of time, observing how these elements interact and evolve. One of the key tools in refining these simulations is the ability to adjust initial conditions, such as the density of matter and the rate of expansion. By running numerous simulations with different parameters, scientists can explore a variety of potential scenarios, watching how galaxies cluster, cosmic filaments form, and massive voids appear within the cosmic landscape. Through this approach, simulations provide crucial insights into the formation of the universe's intricate web of galaxies and large-scale structures. However, simulations are not conducted in a vacuum. To validate these theoretical models, scientists compare their simulation outcomes with real astronomical observations. A critical point of reference is the cosmic microwave background radiation, often referred to as the afterglow of the Big Bang. This radiation is a faint, pervasive signal that fills the entire universe, carrying vital information about the early conditions of the cosmos. By aligning theoretical predictions with observational data from this background radiation, researchers are able to refine their simulations and improve their models of cosmic evolution. The cosmic microwave background serves as a kind of snapshot of the universe when it was just a few 100,000 years old, capturing the conditions of a time shortly after the Big Bang. As the universe expanded and cooled, the initially hot energy of creation was stretched and transformed into microwaves, providing a cosmic imprint of the universe's infancy. The study of these radiation fluctuations is crucial because they reveal the density variations that existed in the early universe. These fluctuations were key to the formation of galaxies and larger cosmic structures, with areas of slightly higher temperature corresponding to regions where matter began to clump together, eventually leading to the creation of stars, galaxies, and clusters of galaxies. Beyond their role in tracing the formation of cosmic structures, the cosmic background radiation also provides researchers with a way to probe the fundamental characteristics of the universe itself. By studying its temperature and anisotropies, small irregularities in its distribution, scientists can glean critical insights into some of the universe's most fundamental properties. For instance, the radiation helps to determine the rate of expansion of the universe, its age, and even the types of matter that compose it. This relic of the early universe continues to be a vital source of information, shedding light on both the origins and the ongoing evolution of the cosmos. The universe, vast and ever-expanding, remains a realm of both awe and mystery. With each new discovery, we edge closer to understanding its true nature, but there is still much to explore. The future of cosmology holds the promise of revelations that could dramatically alter our current perceptions. Imagine the universe as a balloon that is continuously inflating, a simple but powerful analogy that reflects the ongoing expansion of space itself. For many years, it was believed that beyond the observable cosmos lies nothingness. Yet, emerging insights from recent advancements in observational technology suggest that the edges of the universe may be far more complex and intricate than previously imagined. New telescopes, for example, have the potential to reveal cosmic phenomena that are currently hidden from our view. These could include subtle variations in the cosmic microwave background, patterns that may unlock new information about the shape of the universe and how it might curve back on itself. Such findings would challenge our basic understanding of the universe's boundaries and offer a radically different view of what lies beyond the observable realm. If the universe is indeed finite but unbounded, its true structure may not be limited by an edge or an end, but instead may reveal an interconnected, looping expanse that defies our current conception of space. Furthermore, the ongoing investigation into dark matter and dark energy is central to our understanding of the universe's future and its ultimate fate. These mysterious, invisible components appear to be driving the accelerated expansion of the universe, suggesting that the very fabric of space is expanding at an ever-increasing rate. If these phenomena continue to exert their influence, it would indicate that the universe's boundaries are not static, but are instead constantly shifting, evolving in ways we have yet to fully comprehend. By unraveling the secrets of dark matter and dark energy, scientists may be able to redefine the geometry and dimensions of the universe itself. This could lead to a profound shift in how we view the cosmos, expanding our understanding of what lies beyond the limits of our observable universe and opening new avenues for exploration in the vast, mysterious expanse that continues to unfold before us. Astrophysics has been experiencing a series of monumental breakthroughs that could completely redefine our understanding of the cosmos. One of the most groundbreaking discoveries is the detection of gravitational waves, subtle ripples in space-time that were first predicted by Einstein over a century ago. These waves provide us with the rare opportunity to study some of the most violent and distant events in the universe, such as the collisions of black holes or neutron stars. Their detection not only confirms long-standing theoretical predictions, but opens the door to understanding how distant galaxies interact. Furthermore, the insights gained from gravitational waves could offer a deeper understanding of the very fabric of space itself, shedding light on its elusive properties and dynamic nature. This might eventually lead to the development of entirely new theories, including those surrounding the concept of the multiverse, the possibility that an infinite number of universes exist alongside our own. As researchers continue to push the boundaries of human knowledge, they are aided by cutting-edge technologies and an insatiable curiosity that drives global collaboration. Each new discovery brings us a step closer to constructing a more complete picture of the universe's vast expanse. In this constant pursuit of understanding, it is as if we are adding pieces to a cosmic puzzle, one that could ultimately compel us to rethink not just our theories, but our very place in the grand scheme of existence. With every new piece of the puzzle, we are inching closer to unraveling mysteries that were once thought to be beyond our grasp. And with these revelations, we may find ourselves not only reconsidering our role in the universe, but also realizing that there is so much more to explore beyond the stars, expanding our view and reshaping our perception of the cosmos. Despite centuries of exploration and discovery, the universe remains a vast tapestry of mysteries, some of which continue to elude our understanding. One of the most profound of these mysteries is dark matter, an invisible substance that seems to make up a significant portion of the universe's total mass. Although its presence can be inferred from its gravitational effects on galaxies, we are still in the dark about its exact nature. Is it made of known particles, or does it consist of something entirely new, something that might fundamentally challenge our current understanding of physics? Alongside dark matter stands the enigma of dark energy, an invisible force responsible for the accelerated expansion of the universe. Unlike dark matter, which is hypothesized to exist due to its gravitational pull, dark energy appears to be driving galaxies apart, making it one of the most puzzling phenomena in modern astrophysics. Its exact properties and effects remain largely hypothetical, and understanding it could unlock new insights into the fate of the cosmos. Another question that continues to baffle researchers is that of cosmic inflation, a theory suggesting that the universe underwent an exponential expansion in the moments following the Big Bang. While the theory helps explain the uniformity of the cosmos, it raises more questions than it answers. What caused this rapid inflation, and how did it shape the early universe? Moreover, we still lack definitive evidence regarding the precise mechanisms that drove this expansion, as well as what happened before this sudden growth began. The very existence of inflation challenges our assumptions about space and time, and understanding its true nature is crucial to piecing together the early history of the universe. The mysteries of black holes, those enigmatic regions of space where gravity becomes so intense that not even light can escape, represent another major area of exploration. Despite their importance, black holes remain one of the greatest puzzles of modern astrophysics. As scientists probe deeper into their behavior, they are confronted with a host of difficult questions, ranging from the nature of the so-called information paradox, which suggests that information falling into a black hole may be lost forever, to the fundamental issue of whether black holes can be described by conventional physics. The very question of what occurs at the singularity, the point at the center of a black hole where gravity becomes infinitely strong, remains an unsolved mystery. Beyond the fundamental mysteries of dark matter, dark energy and black holes, there lies the grand question of the structure of the universe on its largest scales. The cosmos as we know it is not a static entity, but a dynamic and ever-evolving collection of galaxies and vast empty voids. The universe itself forms an intricate web of cosmic filaments and voids, but how these structures emerged and evolved over time is still not fully understood. Scientists are tirelessly investigating why the universe is structured the way it is, why galaxies are arranged in particular patterns, and what factors led to the formation of these cosmic threads. As each new discovery sheds light on these questions, it tends to open up even more questions, urging researchers to dig deeper and consider new possibilities. The quest to unlock the secrets of the universe's structure is far from over, and it promises to reveal wonders beyond our current comprehension. The idea of the universe's edge has long captured the imagination of both scientists and the general public. For centuries, the prevailing belief was that the universe was akin to a vast balloon, expanding outward from a central point with a clear and defined boundary. However, recent advancements in cosmology and observational techniques are beginning to challenge this notion. If we look up at the night sky, we are not merely observing what exists at this very moment. Instead, the light from distant galaxies carries with it a snapshot of the universe as it was billions of years ago, offering a glimpse into its past. Future telescopes, equipped with ever more advanced technology, will allow us to peer deeper into space than ever before. By capturing light that has traveled for billions of years, we may be able to study the universe in its infancy, when it was only a tiny fraction of its current size. As we continue to expand the frontiers of our exploration, it's becoming increasingly apparent that the edge of the universe might not be a physical boundary at all. Instead, it may represent the limits of our observational capacity, the furthest point that we can observe based on the technology available to us. What lies beyond this observable universe remains unknown, but the continued study of phenomena like cosmic microwave background radiation, along with a deeper understanding of the distribution of galaxies, may one day provide us with clues about the universe's true shape and dimensions. It's even possible that the universe is infinite, stretching endlessly without any discernible boundary. This idea is further complicated by theories such as cosmic inflation, which suggests that the universe underwent a rapid expansion shortly after the Big Bang. If this theory is correct, our observable universe is merely a small slice of a much larger reality, one that may stretch far beyond our current understanding. Advances in technology are crucial to overcoming the many challenges involved in exploring the universe's limits. One of the greatest hurdles is the sheer scale of the cosmos itself. The universe is so vast that only a tiny fraction of it is within our reach, with most phenomena occurring outside the range of even our most advanced instruments. The observable universe represents just a small portion of the whole, and gathering data from beyond this observable region is a daunting task that requires innovative solutions. Furthermore, the current laws of physics, relativity, and quantum mechanics, while incredibly powerful, are often incompatible when we probe the extremes of the cosmos, such as inside black holes or during the first moments of the Big Bang. Reconciling these two pillars of physics into a single, unified theory remains one of the biggest challenges facing modern science. In addition to these theoretical hurdles, there are practical challenges as well. Technology has made tremendous strides in improving our ability to observe distant galaxies, black holes, and other phenomena, but there are still significant limitations. The detection of dark matter and dark energy, for example, requires instruments that are still in the early stages of development. Furthermore, deep space exploration, sending probes and missions to the farthest reaches of our solar system and beyond, is a resource-intensive and complex endeavor. As we collect more data, scientists are faced with the challenge of interpreting it, often leading to new questions rather than clear answers. Ultimately, the universe is a deeply complex and mysterious entity, and the processes that govern it occur on timescales and spatial scales that are difficult to comprehend. As technology advances and our understanding deepens, we continue to grapple with questions that may forever elude a complete answer. The journey to understand the universe's boundaries is far from over, but each step forward brings us closer to unlocking the secrets of existence itself. The philosophical implications of understanding the universe's limits are vast, stirring profound questions that challenge our very conceptions of existence, reality, and our place in the cosmos. As scientists probe deeper into what lies beyond our observable horizon, new layers of complexity unfold. These questions not only push the boundaries of science, but also spark rich debates about the fundamental nature of reality, influencing both scientific paradigms and our understanding of life itself. The effort to comprehend the universe's limits is a multifaceted endeavor. It integrates technological advances, theoretical frameworks, observational techniques, and philosophical insights. Each challenge we face in this pursuit represents an opportunity for growth and discovery, gradually pulling humanity closer to the mysteries that have long eluded us. With every new finding, we inch closer to unraveling the enigma of existence, building upon each discovery to better understand the vastness of the cosmos. Imagine staring into a black void and, unexpectedly, encountering a treasure trove of cosmic wonders. The potential discoveries awaiting us in this uncharted territory are immense, each discovery offering a glimpse into the unknown that extends far beyond our current knowledge. One of the most profound revelations could involve the detection of extraterrestrial life. Finding microorganisms or even more complex beings beyond Earth would radically challenge our understanding of biology, forcing us to reconsider the resilience and adaptability of life itself. Such a breakthrough would not only answer the age-old question of whether we are alone in the universe, but would also spark new inquiries into the conditions necessary for life, its potential for survival, and the mechanisms of its evolution. Another groundbreaking discovery could emerge from our study of dark matter and dark energy, the mysterious substances that account for most of the mass and energy in the universe. If scientists were to successfully identify the particles constituting dark matter, or uncover the true nature of dark energy, it would lead to a monumental shift in our understanding of the universe. This knowledge would provide us with insights into the fundamental workings of reality, possibly revealing the universe's future trajectory and reshaping our entire understanding of physics. The detection of gravitational waves, which has already provided profound insights into cosmic events such as black hole mergers and supernova explosions, offers a fascinating glimpse into the universe's hidden past. With more advanced detection methods, we could uncover an entirely new layer of the universe's history, capturing echoes from the events that shaped cosmic evolution. These discoveries could challenge existing theories about the Big Bang and the subsequent development of cosmic structures, forcing us to reevaluate our models of the universe's origins. Exploring extreme environments such as the icy moons of Jupiter and Saturn could yield even more unexpected revelations. For instance, detecting subsurface oceans teeming with life or complex organic materials would dramatically broaden our understanding of habitability and the conditions under which life might emerge. Such findings would not only enrich our understanding of astrobiology, but also expand the search for life beyond our planet, suggesting that the universe might harbor far more diverse environments than previously imagined. In addition, breakthroughs in quantum physics could fundamentally alter our perceptions of space and time. Unlocking the mysteries of quantum entanglement or finding ways to create stable forms of wormholes might open up new avenues for interstellar travel, communication, and even a deeper understanding of the very fabric of reality itself. If we were to harness the power of quantum mechanics to manipulate space-time, we could revolutionize not just our technologies, but also our conceptualization of the universe, enabling us to explore new dimensions of existence that were once thought to be pure science fiction. As we venture beyond the observable universe, we enter a realm rich with speculation and imagination. One possibility that has captured the imaginations of physicists and philosophers alike is the concept of a multiverse, suggesting that our universe is just one of many, each with its own unique laws of physics and dimensions. In such a scenario, other universes could exist with fundamentally different physical laws, where forces behave in ways we cannot yet comprehend, or entirely new types of matter might be found. Such an idea challenges the very nature of our reality, suggesting that the universe we know may just be a small part of a much grander and more complex multiverse. Another captivating possibility lies in the existence of cosmic structures beyond our current observational capacity. For instance, the concept of a dark universe populated entirely by dark matter and dark energy raises the intriguing idea of an invisible realm that does not interact with light and is undetectable by our current instruments. This hidden expanse might be filled with phenomena that defy our comprehension, where the laws of space and time might function in ways radically different from our own universe. These dark structures could hold the key to understanding the true nature of reality, offering a glimpse into a realm that remains beyond our reach, yet intimately connected to the universe we observe. Theories also propose the existence of higher dimensions, extraspatial dimensions that transcend the three we experience in our daily lives. These higher dimensions might be home to entirely new forms of matter and forces, giving rise to exotic phenomena like gravitational anomalies or new methods of communication that bypass traditional physical laws. The exploration of these higher dimensions could not only change the way we perceive reality, but could also lead to the discovery of entirely new technologies and modes of existence that defy our current understanding of the universe. Perhaps most tantalizing of all is the speculation about advanced civilizations residing in these other realms, capable of manipulating space and time in ways we cannot yet conceive. These extraterrestrial beings could possess technologies or abilities far beyond our own, offering us a glimpse into the potential future of human civilization, or even providing the keys to unraveling the deepest mysteries of the cosmos. The possibilities for interaction with such advanced entities spark the imagination, laying the groundwork for scenarios reminiscent of science fiction, where humanity ventures into new realities, grapples with alien intelligence, and discovers how our existence fits into the larger cosmic story. Cosmic strings, another fascinating theoretical concept, could also hold crucial insights into the universe's evolution. These incredibly thin yet dense objects, stretching across vast distances in space, are believed to be remnants from the early universe, formed during phase transitions that marked pivotal moments in the universe's infancy. The study of cosmic strings can offer us a deeper appreciation of the fabric of space-time itself. These hypothetical objects possess immense mass per unit length, creating powerful gravitational effects that could warp space around them in a manner similar to the way a heavy ball distorts the surface of a trampoline. Such distortions could potentially alter the path of light and influence the motion of other celestial bodies, helping us understand the large-scale structure of the universe and the distribution of galaxies. Despite the fact that cosmic strings have not yet been detected, their conceptual importance is undeniable. They may help explain the distribution of galaxies and the nature of cosmic expansion, providing a new lens through which to understand the universe's formative moments. As research into these theoretical objects continues, we are drawn deeper into the questions of how the early universe set the stage for the complex systems we observe today. Beyond cosmic strings, the existence of exotic forms of matter could play a pivotal role in our understanding of the vast and uncharted regions that lie beyond our observable universe. Exotic matter, substances that behave in ways vastly different from the known forms of matter, could unlock new insights into the functionality of cosmic structures invisible to our current instruments. Imagine a universe where gravity behaves differently, or where the fundamental forces operate in ways that challenge everything we know. Dark matter, one of the most elusive forms of exotic matter, might be key to understanding these phenomena. Dark matter does not emit light or energy, making it incredibly difficult to detect with traditional tools. However, it is believed to make up a significant portion of the universe's mass and plays a crucial role in the motion of galaxies and galaxy clusters, extending far beyond the range of our current telescopes. By studying dark matter, we could gain insight into the formation and stability of galaxies that stretch beyond our observational reach, offering a new dimension to our understanding of the universe's large-scale structure. Moreover, the concept of negative mass adds another layer of intrigue. If such material exists, it could interact with gravity in unusual ways, potentially allowing the creation of wormholes or other exotic phenomena that offer alternative pathways through space-time. This could have profound implications for the evolution of cosmic structures and the development of the universe beyond the observable realm. By studying such exotic matter, we could unlock the secrets of how the universe's vast web of galaxies and cosmic structures evolves, further shaping our understanding of the universe's vast and mysterious expanse. Cosmic inflation, the rapid expansion of the universe just after the Big Bang, is one of the most fascinating phenomena in modern cosmology. As we continue to explore the cosmos, we're discovering more about how exotic matter might influence this early period of rapid growth. This exotic matter, though elusive and difficult to detect, could be a key player in rewriting the rules of cosmic evolution. As scientists delve deeper into this unknown territory, they hope to unlock the secrets of regions that remain beyond our reach, and perhaps even reshape our entire understanding of the universe itself. With each new discovery, we inch closer to understanding the vast forces that govern the cosmos, pushing the boundaries of human knowledge. The universe, as we know it, is vast, intricate, and largely shrouded in mystery. So much of the cosmos lies beyond our grasp, hidden in regions so distant or obscure that they defy direct observation. But these distant areas are not empty spaces. In fact, they are thought to be filled with unknown forces and energies that behave in ways we can only begin to imagine. Imagine, if you will, the universe as a vast, interconnected web, where each part, visible and invisible alike, interacts in complex ways, even with regions that we cannot directly observe or measure. Among these mysterious forces are two of the most intriguing phenomena in modern astrophysics: dark matter and dark energy. Dark matter is an invisible substance that does not emit or reflect light, yet it exerts a significant gravitational influence on the matter that we can observe. While we cannot detect dark matter directly, scientists infer its existence through the effects it has on galaxies and galaxy clusters. These objects, when observed, appear to be influenced by a mass that we cannot see. The movements and behavior of galaxies suggest that something unseen is affecting them, pulling them in ways we cannot explain with visible matter alone. Dark matter may make up a substantial portion of the mass in the universe, yet remains one of the most elusive components of the cosmos. Similarly, dark energy is a mysterious force that appears to be driving the accelerated expansion of the universe. Though we cannot perceive dark energy directly, its effects are felt in the way galaxies move apart, accelerating over time. The evidence for dark energy comes from the observation that the universe is expanding at an ever-increasing rate, a phenomenon that cannot be explained by the forces of gravity alone. Together, dark matter and dark energy are believed to account for most of the mass energy content of the universe, yet their true nature remains a subject of great scientific intrigue and exploration. As we study these forces, we are reminded of how much we still have to learn about the cosmos. In addition to dark matter and dark energy, there are other forces at play in the universe. Gravitational waves, for example, are ripples in the fabric of space-time that were first predicted more than a century ago. These waves, caused by massive objects like black holes or neutron stars colliding or merging, were only recently detected by advanced observatories. Gravitational waves can travel across the universe, carrying with them information about the events that caused them, even from vast distances. Their detection marks a major milestone in our understanding of the universe, revealing a new way to observe cosmic phenomena. As our technologies and detection methods continue to improve, we are getting closer to uncovering the mysteries of these unknown forces and energies. Who knows what remarkable insights await us in the parts of the universe that remain unseen and undetected. The journey into these uncharted realms holds the promise of reshaping our understanding of the very nature of reality itself, offering new glimpses into the underlying mechanisms that govern the cosmos. Measuring distances in the vast expanse of the universe is no simple task. It requires a variety of techniques, each suited to different scales and situations. For relatively nearby stars, astronomers often use a method known as parallax. Parallax involves observing an object from two different points in the Earth's orbit around the Sun. Just as your thumb appears to shift against the background when you close one eye and then the other, distant stars appear to shift in position when viewed from two different locations on Earth's orbit. By measuring this apparent shift and knowing the distance between the two observation points, astronomers can calculate the distance to the star. This technique is highly effective for nearby stars, but as we move farther from home, things become more complex. As we venture beyond the Milky Way, measuring distance becomes much more challenging. One of the most important tools astronomers use to measure far-off objects is the concept of standard candles. Certain types of stars, particularly supernovae, have well-known brightness patterns. By observing the brightness of a supernova from Earth, scientists can determine its distance. If a supernova appears dimmer than expected, it must be farther away. If it looks brighter, it is closer. This technique is invaluable for measuring the distance to distant galaxies and other cosmic objects. For even more distant galaxies, those billions of light years away, astronomers rely on the redshift phenomenon. As the universe expands, light from distant galaxies stretches, shifting toward longer wavelengths. This redshift is similar to the sound of a train whistle becoming lower as the train moves away from you. By measuring how much the light from a galaxy has shifted toward the red end of the spectrum, astronomers can infer how far away the galaxy is. These methods, combined with increasingly advanced technology and observations from telescopes sensitive to a variety of wavelengths, allow scientists to measure the incredible distances between us and the farthest reaches of the universe. However, measuring these cosmic structures presents several significant challenges. The sheer distances involved are mind-boggling, and light takes an incredibly long time to travel from distant objects to our telescopes. This means that when we observe these far-off galaxies, we're not seeing them as they are today, but rather as they were when the light first left them. This delay complicates our understanding and requires astronomers to interpret images within a historical context. Additionally, the faintness of distant objects is another major hurdle. As light travels across the vastness of space, it weakens, making it difficult to detect remote galaxies, star clusters, and other cosmic phenomena. To overcome this, astronomers rely on powerful telescopes, many of which are equipped with advanced technologies like multiple exposures or specialized filters. These tools help capture more light, enhancing the visibility of distant objects. However, the challenges don't end there. Between us and these far-off objects lies a great deal of cosmic material, gas, dust, and even dark matter. These materials can absorb and scatter light, further complicating the accuracy of our observations. Understanding how these intervening elements affect light propagation is crucial for correcting the data we collect and ensuring that we accurately deduce the true nature of the distant objects we observe. In the end, the universe remains an incredible, vast mystery, and our understanding of it is still in its infancy. Every discovery, every breakthrough in technology or observation brings us closer to unraveling the fundamental forces that shape our cosmos. Yet, for all that we know, there is still so much more to uncover. As our methods advance and our curiosity continues to drive us forward, we can only wonder what remarkable insights await us in the far reaches of the universe, just beyond our current sight. The universe, in its sheer complexity, is far from static. It is constantly evolving and expanding, an idea that challenges our understanding of space and time itself. This expansion gives rise to a phenomenon known as redshift, a process in which light from distant celestial objects stretches as it travels across vast distances. The light's wavelength lengthens, shifting it toward the red end of the spectrum, and in turn reduces its energy. This stretching effect makes it difficult to measure exact distances and sizes of distant objects, adding a layer of uncertainty to our cosmic measurements. It's a constant reminder that the universe's scale defies our natural instincts to understand it in familiar terms, turning what should be straightforward into an intricate puzzle that requires deep thought and refined methods to solve. But redshift is only one part of the challenge. The theoretical models we use to make sense of the universe itself are built on assumptions that are often clouded by uncertainty. These models, which underpin much of our understanding of the cosmos, rely on simulations and cosmological theories to predict the behavior of galaxies, stars, and other cosmic structures. However, if these models don't accurately mirror the actual behavior of the universe, our measurements and assumptions could lead us down the wrong path, causing us to misinterpret the data or overlook crucial details. It is a delicate balance between observation and theory, one that requires constant calibration. Each new discovery, be it from a telescope, a space probe, or a deep sky survey, must be carefully reconciled with what we already know. This ongoing process of refinement ensures that our knowledge of the universe is always evolving, even as the cosmos itself undergoes its own continuous transformation. Navigating these complexities requires creativity and resilience. As we push the boundaries of what's possible, scientists and researchers are driven to develop innovative technologies and methods that allow us to peer deeper into space. These advances open new windows into the universe, giving us glimpses of the distant and the unreachable. One of the key ways we begin to understand the immense distances in the universe is through light-year measurements. A light-year is the distance that light can travel in 1 year, which equals an astonishing 5.88 trillion miles. Considering how incredibly fast light moves, a single light-year represents a truly vast distance. When we observe distant stars and galaxies, the light we see has often traveled for years, decades, or even millions of years to reach us. This means that when we gaze into the night sky, we are not simply observing the current state of those objects. Instead, we are seeing them as they were in the past, often long before human civilization even began. For example, if a star is located 10 light years away from Earth, the light we are seeing today left that star 10 years ago, giving us a snapshot of its history. This delay between emission and reception of light allows astronomers to essentially look back in time and trace the evolution of distant cosmic objects. By using light years as a measurement, astronomers are able to map the vastness of the universe. They can compare the distances between galaxies, stars, and other celestial bodies, placing our own galaxy, our Milky Way, within a much larger cosmic context. These measurements highlight not just the physical distances between objects, but also the immense time it takes for light to travel across these stretches of space. This understanding helps us conceptualize a universe that, on any human scale, is practically infinite. The concept of light years, therefore, is not just a technical measurement. It is a tool that allows us to comprehend the immensity of the cosmos and the intricate dance of light and time that shapes our observations. At the heart of our understanding of cosmic expansion lies the Hubble constant, a fundamental indicator of how fast the universe is stretching. To visualize this, imagine the universe as a balloon filled with air. As the balloon inflates, every point on its surface moves away from the others. The Hubble constant measures this rate of expansion, quantifying the speed at which galaxies are receding from one another as space itself grows. The key insight of this relationship is that the farther away a galaxy is from us, the faster it appears to be moving away. This correlation is vital because it allows astronomers to trace the expansion of the universe backward in time, suggesting that at one point, the universe was compressed into an infinitesimally small space before expanding outward, eventually leading to the vast cosmos we observe today. This expansion is a sign that the universe is far from static. It is dynamic, constantly evolving. The value of the Hubble constant provides important clues about the universe's overall geometry and its eventual fate. By studying how the constant changes over time, astronomers can make predictions about whether the universe will continue expanding indefinitely, reach a stable size, or eventually collapse back in on itself. This provides an essential framework for understanding not just the size of the universe, but also its nature and ultimate destiny. The Hubble constant, therefore, is much more than just a number. It is a key to unlocking the mysteries of cosmic history and future. Throughout human history, major discoveries have continually expanded our understanding of the universe's scope. Early astronomers, with their simple telescopes, were the first to look beyond Earth and uncover distant celestial bodies. This shift in perspective, from a geocentric to a heliocentric model, was revolutionary. It set the stage for centuries of further exploration, each discovery opening new doors to our understanding of the cosmos. As technology advanced, so too did our ability to explore further and deeper into space. The invention of more powerful telescopes allowed astronomers to glimpse galaxies, nebulae, and star systems far beyond our own, revealing a universe filled with vast structures and intricate details. The advent of space exploration took our understanding to a whole new level. Robotic probes sent to the outer planets revealed fascinating details about their atmospheres, moons, and geological features. Discoveries like the icy geysers of Enceladus and the diverse landscapes of Mars hinted at the possibility that the building blocks for life could be more widespread than we once thought. These findings have spurred scientific speculation about the potential for life beyond Earth, fueling our curiosity and encouraging further missions into the outer reaches of the solar system. One of the most significant discoveries in recent history came with the detection of cosmic background radiation, which provided strong evidence for the Big Bang theory. This discovery confirmed that the universe had originated from an infinitely small and hot state and has since expanded into the vast cosmos we now observe. Even more surprising was the realization that the observable universe may be just a small fraction of the entire universe, which could extend far beyond what we can currently detect. The discovery of exoplanets, planets orbiting stars far from our own solar system, has further expanded our understanding. Thousands of exoplanets have been found, many of which reside in the habitable zone, a region where conditions may be just right for liquid water to exist. This has led to exciting new possibilities for the existence of life elsewhere in the universe, challenging our assumptions about where life might thrive. At the same time, theories of dark matter and dark energy, two mysterious forces that influence the structure and expansion of the universe, suggest that the majority of the cosmos remains hidden from our view. Though we cannot see these forces directly, their effects on cosmic structures are undeniable. Dark matter and dark energy make up the majority of the universe's mass and energy, yet we understand them only in the most abstract terms. As scientists develop new tools and technologies, they continue to refine our understanding of these enigmatic elements, pushing the boundaries of what we know and can observe. Every discovery, every technological advancement challenges our preconceived notions of the universe. With each new piece of evidence, we are forced to reconsider where the universe begins and where it ends. Our journey into the cosmos is not just about finding the limits of our knowledge, but about continuously redefining those limits as we reach further into the unknown. The exploration of space and the expanding knowledge that accompanies it reveals a universe that is far larger, more complex, and more mysterious than we ever imagined. One that constantly invites us to explore, discover, and learn. The journey to explore the observable universe has been a path marked by groundbreaking milestones, each one pushing the boundaries of human knowledge and transforming our understanding of the cosmos. One of the most significant leaps came in the early 20th century, when astronomers began to realize that the universe was far larger than the confines of our own galaxy. This discovery, which marked a major shift in our perspective, began with the observations of Edwin Hubble. Hubble's work revealed something truly extraordinary. Distant galaxies were moving away from us. This observation suggested that the universe was not static, but rather expanding, a notion that challenged long-held beliefs about the universe's nature and structure. Hubble's revelation about the expanding universe was one of the key pieces of evidence that led to the formulation of the Big Bang theory, which provided an explanation for the universe's origin. It proposed that the universe began from a singular point of unimaginable density and has been expanding ever since. This idea radically shifted our understanding, suggesting that everything in existence, matter, energy, space, and time, had originated from this cataclysmic event. As the universe expanded from this dense state, it began to cool, creating the conditions that would allow galaxies, stars, and planets to form. With advancements in technology, humanity's ability to peer deeper into the cosmos expanded alongside our theoretical frameworks. The development and deployment of powerful telescopes allowed astronomers to see further and more clearly than ever before. Space-based observatories like the Hubble Space Telescope provided breathtaking images and invaluable data, unfettered by the distortions of Earth's atmosphere. Hubble's observations not only revealed stunning views of distant nebulae and galaxies, but also opened up new insights into the nature of dark matter and dark energy. These two mysterious components, which together make up about 95% of the universe, continue to be among the most perplexing and elusive aspects of modern cosmology. As technology progressed, the field of radio astronomy emerged as another crucial tool for exploration. By capturing the radio waves emitted by distant celestial objects, astronomers were able to uncover a wealth of information about the structure and behavior of stars' pulsars and quasars. This breakthrough allowed us to study regions of space that were previously obscured by invisible light, unveiling secrets about the most energetic and violent processes in the universe. It was during this time that scientists made another monumental discovery: the cosmic microwave background radiation. This faint remnant of the early universe provided an essential glimpse into the conditions that existed shortly after the Big Bang, helping to piece together the puzzle of the universe's origins. In more recent decades, technology has allowed us to extend our reach even further, providing the tools necessary to detect exoplanets, planets located outside our solar system. The Kepler mission in particular has unveiled thousands of such worlds, dramatically expanding our understanding of planetary systems and their potential to support life. These discoveries suggest that planets are not unique to our solar system. They exist in a staggering variety of environments across the universe. Some of these exoplanets orbit stars similar to our Sun, while others circle smaller, cooler stars, each presenting new possibilities for the emergence of life. The discovery of exoplanets has opened up a realm of questions about the conditions required for life to exist. Observations have shown that many of these planets lie within their star's habitable zone, where the conditions are just right for liquid water to exist, one of the key ingredients for life as we know it. This has sparked new debates and research into the nature of life itself, encouraging us to reconsider the environments in which life could potentially arise and thrive. Yet, it is not just the discovery of distant planets that has altered our view of the cosmos. Advances in gravitational wave detection have provided an entirely new window into the universe. For the first time, scientists could directly observe the ripples in space-time caused by cataclysmic events, such as the collision of black holes. These groundbreaking observations have provided tangible evidence for phenomena that were once only theoretical, opening up new realms of study about the most extreme conditions in the universe. Each of these discoveries, the expanding universe, the nature of dark matter and energy, the identification of exoplanets, and the detection of gravitational waves, represents a crucial step forward in our ongoing quest to understand the cosmos. Together, these milestones reveal a universe that is far more dynamic, mysterious, and interconnected than we ever imagined. Through visionary theories, technological innovation, and international collaboration, the story of our universe continues to unfold, one discovery at a time. The realization that the universe is expanding had profound implications not just for the field of astronomy, but also for our broader philosophical and scientific outlook. Before Hubble's observations, many astronomers believed in a static universe, one where galaxies existed in a fixed arrangement. The discovery that galaxies were receding from us, at speeds proportional to their distance, completely shattered this view. The idea of a dynamic, evolving universe gradually took hold, leading to a revolutionary shift in the way we think about the cosmos. Hubble's observations provided the empirical evidence needed to support the idea of the Big Bang. This theory postulated that the universe had a beginning, an origin point from which it has been expanding ever since. In this new framework, the universe's history could no longer be viewed as a series of isolated events, but as part of a vast unfolding process. The universe was no longer a static, eternal entity, but a dynamic, evolving one, shaped by forces of gravity, energy, and the passage of time. The concept of an expanding universe also raised important questions about its ultimate fate. Would the expansion continue forever, gradually slowing as galaxies drift farther apart? Or would it eventually reverse, causing the universe to collapse in on itself in what is known as the Big Crunch? These debates prompted further inquiries into the nature of dark energy, a mysterious force believed to be driving the expansion of the universe, and the role it plays in the universe's future. The discovery of the expanding universe also prompted a reevaluation of other cosmic theories, particularly those related to gravity, dark matter, and dark energy. Gravity, which pulls matter together, seemed to work in opposition to dark energy, which is believed to drive the accelerated expansion of the universe. Understanding how these forces interact and the delicate balance between them has become a key area of research in cosmology, with profound implications for our understanding of the universe's fundamental nature. As the search for exoplanets continues, our understanding of the universe grows more intricate and nuanced. The discovery of thousands of exoplanets, many of which lie within their star's habitable zone, has made us rethink the possibility of life beyond Earth. These findings suggest that the universe may be far more hospitable to life than we once thought. The diversity of planets discovered so far, from gas giants to rocky worlds, illustrates the incredible variety of environments that exist across the cosmos, each one potentially offering a different set of conditions for life to arise. In a sense, the discovery of exoplanets represents a turning point in the search for life beyond our planet. With each new planet discovered, we are reminded that the universe is vast and full of potential, offering countless opportunities for scientific exploration and philosophical reflection. As we continue to expand our understanding of the cosmos, we come ever closer to answering the age-old question, are we alone in the universe? This journey of discovery, marked by new technologies, groundbreaking theories, and an expanding knowledge of the universe, continues to captivate our imaginations and fuel our curiosity. It reminds us that the universe is not a distant, immutable object, but a dynamic, evolving entity filled with mysteries waiting to be unraveled. As we stand on the shoulders of those who came before us, we look forward to the discoveries yet to come, knowing that each new revelation will bring us closer to understanding our place in the vast cosmos. Moreover, as our understanding of space deepens, the exploration of exoplanetary atmospheres has revealed extraordinary and tantalizing findings. Scientists have discovered gases in the atmospheres of distant planets that could potentially be signs of biological processes, sparking a wave of curiosity about the kinds of life forms that may arise in the vast and diverse range of planetary environments across the universe. This discovery is not just an isolated finding, but one that compels a far-reaching investigation into the very nature of life itself, what it is, how it begins, and where else it might exist beyond our home planet. Such revelations have profound implications, not just for biology, but for our understanding of the processes that govern the formation and evolution of planets. With each new exoplanet discovered, especially those with unique or unexpected features, the scientific community faces the challenge of refining or even completely overhauling previous models of planetary formation. These discoveries, while sometimes disrupting existing theories, also offer invaluable opportunities to enhance our knowledge of the cosmos. Every new data point strengthens our view of the universe as a place of endless variety, constantly reshaping our understanding of the physical and biological possibilities that exist beyond the Earth. As we explore these new worlds, the questions that arise challenge us to broaden the scope of our imagination. We find ourselves confronted with possibilities that transcend the limits of our traditional frameworks. With each exoplanet discovered, we don't just gain a piece of data about the universe, we are confronted with the immense potential it holds, new frontiers to be explored, new possibilities to be understood. This dynamic, ever-evolving picture of the cosmos invites humanity to dream bigger, to imagine what could lie beyond our current capabilities, and to think more broadly about the universe as an unexplored frontier, waiting for us to reach out and discover its secrets. Equally important in advancing space exploration is the role of international collaboration. The vast complexity and scale of space missions demand that nations come together, pooling their expertise, resources, and diverse perspectives. When countries unite for a space mission, the combined strengths often lead to innovative breakthroughs, skating, offering solutions to challenges that would be insurmountable for any single nation to tackle alone. Different nations bring specialized technologies, advanced materials, and unique insights that, when shared, create superior spacecraft and scientific instruments capable of performing far beyond what could have been achieved in isolation. Moreover, the high cost of space exploration further highlights the need for international partnerships. Space missions are expensive endeavors, requiring vast amounts of funding, technology, and human resources. By sharing these costs, countries can undertake missions that would otherwise be impossible to execute on their own. This not only makes space exploration more accessible, but it also strengthens the collaborative bond between nations, fostering a sense of unity and shared purpose. The collective pursuit of knowledge about our universe becomes a symbol of peaceful cooperation, reminding us that space exploration is a venture that belongs to all of humanity. These partnerships are not just about sharing financial burdens, they are about building a global community, a community that, through collaboration, fosters peace, understanding, and respect between nations. In a world that often seems divided, the international efforts to explore space offer a rare opportunity for cooperation on a truly global scale. It encourages dialogue, nurtures mutual trust, and opens the door for the exchange of ideas and cultures, all of which transcend national borders and divisions. Joint missions also lead to more robust scientific outputs. When researchers from different countries work together, they bring different approaches, methodologies, and perspectives to the table. This pooling of expertise results in richer scientific discussions, more innovative ideas, and accelerated discoveries that push the boundaries of what we know about the cosmos. Through collective intelligence, space exploration benefits from a more multifaceted and integrated understanding of the universe, accelerating progress in ways that might not have been possible without these cross-border collaborations. One of the most visible examples of such collaboration is the International Space Station, ISS. This extraordinary platform is a model of international teamwork, with space agencies from across the globe: NASA, the Russian space agency Roscosmos, the European Space Agency ESA, Japan's JAXA, and Canada's CSA, coming together to operate and manage this state-of-the-art laboratory in orbit. The ISS serves as a platform for cutting-edge scientific research in microgravity, providing researchers with the ability to conduct experiments in areas like biology, physics, and materials science, experiments that would be impossible under Earth's gravity. The work done on the ISS has not only advanced our understanding of fundamental scientific principles, but it has also provided critical insights into human adaptability in space, laying the groundwork for future human missions to distant worlds. By demonstrating how humans can live and work in space for extended periods, the ISS has become an essential stepping stone for humanity's eventual exploration of Mars and beyond. Another excellent example of international cooperation in space exploration is the Mars Exploration Program. The various Mars missions, such as the rovers Spirit, Opportunity, Curiosity, and Perseverance, have been the result of partnerships between NASA and several international collaborators. These missions have radically transformed our understanding of Mars, examining its geology, climate, and the potential for past or present life. Each rover has also contributed to laying the groundwork for future human exploration by identifying resources, assessing potential hazards, and providing critical data about the Martian environment. The Voyager missions, launched in the late 1970s, represent yet another milestone in the annals of global cooperation in space. Voyager 1 and Voyager 2, the farthest human-made objects from Earth, have ventured deep into the outer reaches of our solar system and are now entering interstellar space. Their journey has yielded invaluable information about the gas giants, including their atmospheres, magnetic fields, and moons, and has provided new insights into the nature of our solar system's outer limits. These missions epitomize the power of international collaboration, enabling scientists from around the world to collectively push the boundaries of human exploration and unlock the mysteries of space. Each of these missions and countless others exemplifies how collaboration between nations and scientists can drive progress in ways that no single country could achieve on its own. They illustrate the immense possibilities that open up when humanity unites in pursuit of a common goal, understanding the universe and our place within it. Throughout history, the exploration of the cosmos has been influenced by diverse cultural perspectives, each contributing unique insights into our understanding of the universe. Ancient civilizations, for instance, crafted myths and stories that explain the movements of celestial bodies. These myths were not merely tales, but frameworks for observing and understanding the cosmos. The Babylonians, for example, carefully tracked the movements of planets, creating some of the earliest astronomical records that laid the foundation for the mathematical approaches that would later define astronomy. In ancient China, scholars meticulously observed the night sky, documenting phenomena such as comets and supernovae. These observations were not just scientific records, but also spiritual ones, as the Chinese linked celestial events to cycles of life and changes in society. This holistic approach fostered a tradition of scientific inquiry that emphasized balance and harmony with the universe, a perspective that still influences Chinese thought today. Similarly, many indigenous cultures in the Americas integrated astronomy with their spiritual beliefs. Native American tribes navigated using the stars, creating detailed star maps that guided their seasonal activities and ceremonies. For these cultures, the stars were not distant objects to be studied from afar, but integral parts of their spiritual and practical lives, representing a deep connection between the human experience and the cosmos. The Renaissance marked a pivotal moment in the history of space exploration, when European scholars began to challenge the prevailing understanding of the universe. Figures like Copernicus, Kepler, and Galileo revolutionized the way humanity viewed the cosmos. Their emphasis on observation, experimentation, and questioning of long-held beliefs paved the way for the scientific revolution, which fundamentally changed the way we think about the universe and our place within it. Today, as we look to the future, we are reminded that the exploration of space is not just about technology or discovery. It is about asking fundamental questions about who we are and where we fit in the grand scheme of the cosmos. With each step forward in our understanding, we are not only discovering new worlds, but also expanding the horizons of human imagination, pushing the boundaries of what we thought possible, and connecting with the mysteries of the universe in ways that our ancestors could have only dreamed of. The collaboration of different cultures in modern astronomy is reshaping the landscape of scientific discovery, infusing the field with fresh perspectives and valuable insights. International space missions, which often involve multiple countries, have become a testament to the power of global cooperation, bringing together diverse technologies, expertise, and knowledge from across the world. This synergy allows for the blending of advanced modern tools with ancient wisdom, as traditional knowledge systems, which have long guided humanity's understanding of the cosmos, are being integrated into cutting-edge scientific research. This cultural exchange is a key element in broadening our understanding of the universe, as it emphasizes that exploring the edges of space is not solely the domain of science, but a shared human endeavor deeply rooted in a multitude of cultural traditions. The fusion of global resources in cosmic research has created a powerful, interconnected network that enhances our understanding of the universe. When scientists from various countries collaborate, they pool their expertise, skills, and technologies, enabling them to carry out more comprehensive studies than any one group could achieve alone. This collaborative approach has made possible the development of large-scale projects, such as space telescopes and particle accelerators, which require substantial investment and diverse skill sets. By sharing resources, scientists also avoid duplicating efforts. Rather than multiple organizations working on similar research programs independently, a united initiative can tackle a cosmic mystery more efficiently. This not only accelerates the pace of discovery, but also optimizes the use of time and resources, driving more rapid advancements in the field. Access to shared data from observatories and space missions around the world further enhances the quality of research. Scientists now have the ability to draw from a far broader spectrum of information, helping them make more informed and accurate conclusions. Cultural exchange and collaboration between nations and researchers also foster an environment where new ideas can flourish. Different perspectives drawn from varying methodologies and scientific practices often lead to innovative solutions and breakthrough ideas. This collaborative spirit nurtures creativity, providing novel ways of addressing the vast and complex challenges posed by the universe. The importance of these international collaborations extends far beyond the current scientific generation. The shared commitment to exploration ensures that the benefits of cosmic research are felt by all of humanity, and it serves as a powerful motivator for future generations to continue pushing the boundaries of human knowledge and space exploration. The collective effort of nations and individuals alike inspires hope and curiosity about the unknown, fueling an enduring desire to understand our place in the universe and to reach for the stars. As futurists envision the exploration of the universe's outer limits, they imagine it not as a singular goal, but as a profound journey into the unknown, one that could transform the very essence of human existence. They speculate about the development of advanced technologies that could take humanity far beyond the confines of our solar system. Concepts such as generation ships, massive spacecraft designed to carry people over multiple generations, reflect the idea that while it may not be within our lifetimes to witness the colonization of distant worlds, the foundation laid by current and future space exploration will provide the stepping stones for generations to come. Equally captivating is the speculative idea of faster-than-light travel, a concept that remains firmly in the realm of theoretical physics, but has inspired countless imaginations. Futurists wonder whether it might one day be possible to manipulate the very fabric of space-time, bending it through exotic matter or creating stable wormholes. These technologies would allow travel to distant galaxies in a fraction of the time it takes with our current methods, making the vastness of the universe feel more accessible and within reach. In addition to technological advances, the role of artificial intelligence and autonomous exploration drones is also central to the future of space exploration. These highly capable small machines could be sent to remote corners of space to gather data, map out environments, and scout celestial bodies that are beyond human reach. With their ability to operate independently and transmit information back to Earth, these drones would act as our eyes and ears in far-off regions of the cosmos, collecting valuable data in places where human exploration would be impractical or unsafe. Futurists also emphasize the need for unprecedented collaboration between nations and private enterprises. They envision an interconnected world where governments, scientists, and corporations work together in harmony, pooling their resources and knowledge to tackle the most profound questions of the universe. This collective effort extends beyond just governmental initiatives to include private companies, which are playing an increasingly vital role in the development of space technology and exploration. Beyond the technical and scientific aspects, these futurists also explore the philosophical implications of venturing into the great unknown. They consider what it means to be human in the vastness of space and how the discovery of extraterrestrial life, if it were to occur, could reshape our understanding of existence itself. Such discoveries would bring with them profound ethical questions about how we approach and interact with other forms of life. The intersection of technology, philosophy, and collaboration provides a rich tapestry of considerations, shaping a complex and multifaceted vision of what it means to explore the universe. As humanity stands on the cusp of breaking through into new frontiers, the concept of space tourism is gaining increasing attention. The commercialization of space travel holds the potential to greatly enhance our understanding of the universe as it democratizes access to space. With commercial flights becoming a reality for everyday people, the opportunity for a broader range of perspectives to contribute to space exploration grows significantly. Enthusiastic participants from all walks of life, many of whom have not had the chance to be involved in traditional scientific research, will now be able to engage with and contribute to the field in new ways. This shift towards greater public involvement could lead to innovative ideas and fresh inquiries about the cosmos. As more individuals venture into space, they will have the opportunity to participate in citizen science projects, capturing images of celestial phenomena, or conducting experiments related to the effects of microgravity on the human body. Even the smallest contribution, whether it's an experiment or a piece of data, becomes part of a larger effort to unravel the mysteries of the universe. Through the fusion of diverse cultures, technologies, and ideas, the future of space exploration holds boundless potential. The collaborative nature of modern astronomy not only accelerates the pace of discovery, but also fosters a shared vision for the future, one where all of humanity can work together to explore the infinite reaches of space, understand our place in the cosmos, and inspire generations to continue the quest for knowledge beyond the stars. The growing interest in space tourism has the potential to catalyze significant advancements across the entire space industry. As more people look to venture into the cosmos for leisure, the push for improved space technology and infrastructure intensifies. This heightened demand can lead to increased funding for space research, which directly contributes to groundbreaking developments in spacecraft design, safety protocols, and life support systems. Not only does this make space travel more viable in the short term, but it also fuels long-term goals like interplanetary exploration. As we continue to make strides in space tourism, innovations that were originally conceived for recreational purposes could find themselves being repurposed to support more ambitious scientific missions. These advancements, such as more efficient propulsion systems and reliable life support technologies, may allow us to reach distant planets and moons, opening new frontiers for exploration. In a sense, space tourism could act as a testing ground, preparing us for larger-scale missions to the far reaches of the solar system and beyond. Through the lens of space tourism, we develop a deeper, more profound appreciation for Earth. Those who experience the awe of space firsthand often return with a renewed sense of environmental stewardship. The beauty and fragility of our planet, visible from the void of space, inspires a powerful cultural shift. People who once saw Earth as a familiar, comfortable home begin to view it as an isolated speck in a vast, largely unknown universe. This perspective encourages more people to advocate for preserving our planet, and it also ignites a passion for science and exploration. As a result, space tourism can inspire a new generation to pursue careers in science, technology, engineering, and mathematics, STEM. With fresh minds entering the fields of astrophysics, aerospace engineering, and environmental science, new discoveries become more likely, further accelerating our quest to understand the cosmos. The educational benefits of space tourism are not just theoretical. They are already beginning to shape the careers and aspirations of young people, driving them to push the boundaries of what we know. In parallel with these advancements, science fiction plays an undeniably crucial role in shaping how we perceive the universe and its edges. Science fiction has long been a window into the limitless potential of the cosmos, imagining worlds where the boundaries of space are not only explored but also transcended. These narratives present captivating stories of characters who embark on daring voyages into the unknown, encountering alien civilizations, navigating through wormholes, and overcoming the physical limitations that would otherwise prevent human exploration. By creating imaginative landscapes where stars and galaxies are merely the beginning, science fiction ignites a sense of wonder about space. It invites audiences to contemplate what might exist beyond the observable universe, whether that be distant galaxies, black holes, or dimensions that exist beyond our current understanding. In doing so, these stories challenge our preconceptions about isolation and distance, making the farthest reaches of the cosmos seem more accessible and full of potential. Moreover, science fiction frequently intertwines speculative ideas with real scientific theories, making complex concepts easier to digest. For instance, it often draws inspiration from the theory of relativity, which examines how space and time are interconnected. By transforming such scientific principles into engaging plots, these stories encourage audiences to view the universe as a dynamic, ever-changing environment where the edges are not fixed, but rather fluid and open to exploration. This blend of fact and fiction fosters curiosity, urging people to question the very nature of the universe and our place within it. But science fiction's influence extends beyond just entertaining audiences. These narratives often reflect our collective hopes and fears about technology, existence, and the future. By imagining advanced technologies or extraterrestrial life, science fiction raises vital ethical questions about humanity's role in the cosmos. What responsibilities do we have when exploring new worlds? how do we balance the desire to expand our knowledge with the risks of doing so? These are questions that reflect our societal anxieties about progress and its consequences. For scientists and dreamers alike, these speculative ideas can serve as inspiration, driving innovation and pushing the boundaries of current research. As we dream about the future, we also take steps to make those dreams a reality. Space tourism, by introducing a broad audience to the concept of space exploration, has the potential to inspire the next generation of thinkers who will lead humanity into the unknown. Looking forward, we might find ourselves standing on the threshold of even more profound exploration. As technology advances, future civilizations could venture beyond the observable universe, seeking ways to manipulate the very fabric of space-time itself. Imagine for a moment a future where scientists discover a method to create bubbles in space-time, allowing vessels to travel immense distances that were once thought impossible. These bubbles, sustained by energy and matter harvested from the surrounding environment, could be the key to journeys far beyond the reaches of current space travel. Another intriguing avenue for exploration involves the concept of generation ships. Massive, self-sustaining spacecraft designed to carry entire communities across the stars. These ships could navigate the vast emptiness of space over the course of many generations, evolving with each passing era to meet the challenges of deep space travel. They would be equipped to utilize local resources, ensuring that they remain viable even as they venture farther from Earth. There is also the tantalizing possibility of using quantum mechanics to aid in space travel and communication. By harnessing the strange and powerful properties of quantum entanglement, future civilizations may be able to transmit information instantaneously, overcoming the barrier of distance that currently limits our ability to communicate across vast expanses of space. This could be the breakthrough that enables real-time exploration, where data from distant missions arrives in near real time, vastly enhancing our understanding of far-flung regions of the cosmos. Perhaps most fascinating of all is the concept of artificial wormholes, portals that would allow for instantaneous travel between distant points in space. These theoretical gateways could open the door to realms of the universe that are otherwise unreachable, propelling us beyond the known boundaries of space itself. If such portals could be created, they would not only revolutionize space travel, but also challenge our understanding of time, space, and reality. As we delve deeper into these possibilities, we would likely confront profound philosophical questions about the nature of existence and the limits of human knowledge. As we move toward these futuristic visions, we must acknowledge the risks and the unknowns that come with exploring the cosmos. Each step beyond the boundaries of our understanding is fraught with both excitement and peril, but it is also a testament to the intrinsic human desire to discover, learn, and expand our knowledge. Whether we are looking outward toward distant galaxies or inward toward the core of our own existence, the pursuit of space exploration reflects our unquenchable curiosity about the universe and our place within it. However, observing the edges of the universe presents several daunting challenges. The vastness of space is one of the primary obstacles. The universe is not only staggeringly large, but is also expanding at an accelerating rate. This makes it incredibly difficult to pinpoint where the edge of the universe lies. Moreover, the light from the most distant objects takes billions of years to reach us, meaning that we are always looking at the universe as it existed in the past. This delay complicates our understanding of the universe's evolution and makes it difficult to predict what lies ahead. Another challenge comes from the cosmic microwave background radiation, a faint afterglow from the Big Bang that permeates space. While this radiation offers crucial insights into the early universe, it also obscures our observations of more distant phenomena, making it harder to capture a clear picture of what lies beyond the current limits of our knowledge. These obstacles do not deter us, however. Instead, they fuel our drive to understand the universe's true nature. As technology advances, we inch ever closer to overcoming these barriers, taking us one step further in our quest to explore the vast and mysterious cosmos. And in doing so, we uncover not only the secrets of the universe, but also the limitless potential that lies within humanity's imagination. The quest to unlock the mysteries of the cosmos has always been fraught with challenges, with the faint light from distant galaxies and cosmic structures remaining one of the primary obstacles. In order to capture even a fraction of this elusive light, astronomers must employ highly advanced technology. Telescopes must be incredibly sensitive, and often these instruments are placed in remote regions, far from the interference caused by Earth's atmosphere and the pervasive light pollution of urban areas. This is just the beginning of a long and intricate process that scientists must navigate to peer into the vast expanse of the universe. The development of sophisticated instruments capable of observing a variety of wavelengths is essential for such an endeavor. While visible light provides valuable insights, the universe is not limited to what the human eye can see. Many celestial objects emit light beyond our visible spectrum, including radio and infrared wavelengths. Without the ability to observe across this broader spectrum, scientists would miss crucial data about the nature of distant galaxies, nebulae, and other cosmic phenomena. However, there is another substantial hurdle: the theory of cosmic inflation. This concept suggests that the universe underwent an extremely rapid expansion immediately after the Big Bang, and this expansion continues to affect our observations today. The sheer speed of this expansion means that some regions of the universe are now moving away from us faster than the speed of light. These regions are effectively beyond our reach, receding so quickly that we will never be able to observe them. This phenomenon poses a significant limitation in our ability to fully understand the early stages of the universe's evolution. Adding to the complexity is the mysterious force known as dark energy, which is driving the acceleration of the universe's expansion. This unknown force not only challenges our current understanding of physics, but it also complicates our efforts to measure cosmic distances accurately. The influence of dark energy distorts our models of the universe, making it more difficult to chart its growth and to make precise predictions about its future. In addition to these theoretical challenges, there are practical difficulties in analyzing the data collected by these advanced instruments. The data gathered from distant galaxies can often be misinterpreted due to the presence of cosmic noise. Distinguishing between actual cosmic phenomena and local disturbances, or even the artifacts produced by the very instruments we use to observe the universe, requires painstaking and meticulous analysis. This is a monumental task, as even small errors in data interpretation can lead to incorrect conclusions about the nature of distant celestial bodies. One of the major contributing factors to this challenge is the presence of cosmic dust and gas. These particles play a significant role in shaping our view of the universe. Imagine space as a vast, seemingly endless expanse, not just filled with stars, but also clouds of gas and tiny particles of dust. These particles act as a kind of cosmic fog, scattering and absorbing light from distant objects. The dust is made up of microscopic grains, primarily composed of carbon, silicates, and metals, and is mixed with various gas molecules. When light from a distant galaxy encounters this dust, it undergoes a series of interactions that dim its brightness, making it appear fainter than it truly is. As a result, some galaxies, even those that are far from the edge of the observable universe, may be overlooked or mischaracterized. This is especially true for objects that emit light in wavelengths that are already faint and challenging to detect. In some cases, the presence of cosmic dust can lead to the complete obscuration of these galaxies. In other instances, it may distort the color of the light that reaches us. This phenomenon, known as reddening, occurs when shorter wavelengths of light, such as blue, which are often associated with hot young stars, are absorbed or scattered, leaving longer red wavelengths to pass through more easily. The result is a visual distortion where a galaxy that should appear blue and vibrant might instead appear redder than it truly is. This distortion complicates our ability to classify and study distant galaxies. What might appear to be a red older galaxy could simply be the result of cosmic dust filtering out the higher energy blue light. In this way, our understanding of distant galaxies could be drastically altered by the very particles that fill the space between us and those distant celestial bodies. This means that astronomers must rely on complex techniques and innovative instruments to differentiate between true cosmic phenomena and the interference caused by dust and gas. The uneven distribution of cosmic dust throughout the universe further complicates this task. Some regions of space contain large concentrations of dust, which obscure distant galaxies almost entirely, while other areas may be relatively free of such particles, allowing galaxies to shine through more clearly. This uneven scattering of light means that scientists must be particularly careful in interpreting the data they collect. The dust doesn't just obscure light, it alters the way it behaves. Consequently, understanding the properties and behavior of cosmic dust is vital for unlocking the deeper secrets of the universe, especially when looking beyond our immediate cosmic neighborhood. To combat these observational challenges, astronomers and scientists have been working tirelessly to develop new and groundbreaking technologies. One of the most significant hurdles to observing the universe has been Earth's atmosphere, which distorts and absorbs light from celestial objects. To counteract this, ground-based observatories have been outfitted with adaptive optics technology, which corrects for the blurring effects caused by atmospheric turbulence in real time. This enables clearer, more precise images of distant stars and galaxies, providing astronomers with unprecedented views of the cosmos. Yet, even with these advances, Earth's atmosphere remains a limiting factor. That's why space telescopes, such as the Hubble Space Telescope, have revolutionized our understanding of the universe. By placing instruments beyond the reach of atmospheric interference, scientists gain a much clearer and more detailed view of distant celestial bodies. The upcoming James Webb Space Telescope is set to expand our observational capabilities even further, particularly by observing infrared wavelengths. This opens up new possibilities for studying hidden phenomena, such as the birth of stars and galaxies that are otherwise obscured by cosmic dust and gas. In addition to optical and infrared telescopes, radio astronomy has emerged as a powerful tool in understanding the universe. By using large arrays of radio dishes, scientists can employ a technique known as interferometry, which allows multiple telescopes to work together as a single massive observatory. This method enables astronomers to observe faint signals from the farthest reaches of space with extraordinary precision, allowing for the study of phenomena like black holes, dark matter, and the early universe. Machine learning and artificial intelligence are also playing an increasingly important role in analyzing the vast amounts of data generated by modern telescopes. With the sheer volume of data collected, it's essential to have tools capable of processing and categorizing the information quickly and accurately. AI-driven algorithms can sift through this data, filtering out noise and identifying genuine signals from distant cosmic objects, thereby enhancing our ability to make meaningful discoveries. Another revolutionary approach gaining traction is gravitational wave astronomy. This technique allows scientists to study ripples in space-time caused by massive cosmic events, such as the collision of black holes or neutron stars. Unlike traditional optical telescopes, which detect visible light, gravitational wave detectors can capture these subtle ripples, offering insights into some of the most violent and energetic phenomena in the universe. This method opens up an entirely new way of observing the cosmos, revealing a side of the universe that was previously hidden from view. As these technologies continue to evolve, they push the boundaries of what we thought was possible in our exploration of the universe. Each new advancement brings us one step closer to unraveling the deep mysteries of the cosmos. With every breakthrough, our understanding of the universe becomes more intricate, and our place within it more defined. Through perseverance and innovation, humanity is learning to peer deeper into the cosmos, revealing its many wonders and unlocking the secrets of our vast, ever-expanding universe. Earth's atmosphere plays a crucial role in shaping our visual experience of the cosmos. Imagine trying to view a distant star through a foggy window. The light becomes distorted and the star appears to shimmer. This shimmering is caused by the layers of air, particles, and moisture in Earth's atmosphere, which refract and distort the light from celestial objects. It is most noticeable on clear nights when stars seem to twinkle in the night sky. This atmospheric distortion can make even the clearest of nights a challenge for astronomers seeking sharp, detailed images of distant objects. The solution lies in advanced technologies that can either minimize or eliminate these atmospheric effects, allowing for a more accurate and profound understanding of the universe beyond our planet. Our atmosphere, a protective shield enveloping Earth, plays a vital role in ensuring the survival of life on our planet. One of its key functions is to filter out harmful radiation from the sun, preventing most of this dangerous energy from reaching the surface. This filtration is crucial for life, as it helps safeguard our ecosystems and ensures that we aren't bombarded by the potentially devastating effects of solar radiation. However, while this protection is beneficial, it also introduces a limitation. The very same atmosphere that shields us from harm also restricts our ability to observe certain wavelengths of light, shaping how we perceive the universe. Much of the ultraviolet and infrared light emitted by the sun is absorbed or scattered by the atmosphere, leaving us with only a narrow window of visibility. This means that the majority of the electromagnetic spectrum, beyond the visible light we can see, remains hidden from our naked eyes. As a result, many astronomical events, which could otherwise be fascinating to witness, are simply invisible to us. This creates a natural boundary, one that limits our view of the cosmos and forces us to rely on technological advancements to extend our observational capabilities. In addition to the natural filtering by the atmosphere, environmental conditions such as clouds, pollution, and weather can further complicate our observations. These factors create a veil that can obscure even the brightest celestial objects, making it difficult to observe phenomena that would otherwise be visible under clearer skies. This has driven the development of observatories strategically placed at high altitudes, such as atop mountains or even in orbit, beyond the reach of Earth's atmospheric disturbances. Space telescopes, placed in orbit around the Earth, provide a clear and unobstructed view of the universe, unimpeded by the atmospheric filters that limit our ground-based observations. These telescopes can observe a broader spectrum of light, extending beyond the visible and into the ultraviolet and infrared regions, allowing scientists to gather more data about the universe's secrets. Yet, while Earth's atmosphere offers essential protection, it also presents a range of challenges that shape the way we observe and comprehend the cosmos. These limitations are a reminder of the vastness of the universe, with much of it remaining hidden from our direct view, awaiting exploration through scientific ingenuity and technological advancements. Among the most puzzling and enigmatic aspects of the universe is dark matter, a mysterious substance that constitutes a significant portion of the cosmos' total mass. Although we cannot directly detect dark matter, its existence is inferred through its gravitational effects on visible matter. This invisible substance has a profound influence on the structure of the universe, from the formation of galaxies to the shaping of vast galaxy clusters. Dark matter plays a crucial role in the architecture of the universe, acting as a cosmic scaffolding that holds galaxies and galaxy clusters together. The presence of dark matter is most evident when astronomers observe the rotation of galaxies. They notice that the outer regions of these galaxies spin much faster than would be expected if only visible matter, such as stars and gas, were present. This discrepancy suggests that there is an unseen mass, dark matter, providing the necessary gravitational pull to keep the galaxies intact. The gravitational influence of dark matter extends far beyond individual galaxies, helping to shape the large-scale structure of the universe itself, forming a vast and intricate cosmic web. The distribution of dark matter also sheds light on one of the greatest mysteries in modern cosmology, the extent and boundaries of the universe. Current models suggest that dark matter plays an essential role in shaping the large-scale structure of the cosmos, including the distribution of galaxies and the formation of galaxy clusters. These cosmic structures, like threads in an immense web, are bound together by the gravitational pull of dark matter. However, the full extent of the universe remains unclear. What lies beyond the observable universe, beyond the cosmic horizon, remains a subject of speculation. Could there be additional dimensions, unknown regions, or entirely different structures made of dark matter that we cannot yet detect with our current technology? These questions provoke further exploration into the ultimate fate of the universe. Scientists are investigating how dark matter might influence the universe's evolution, whether it will continue expanding forever, collapse back in on itself, or settle into a stable, static state. These inquiries touch upon the fundamental nature of the cosmos and its long-term future. Dark matter, though invisible, plays a critical role in shaping not only the structure of the universe, but also its destiny. As we continue to unravel the mysteries of dark matter, each discovery brings us closer to understanding the universe's grand design, its hidden corners, and the fundamental forces that govern its existence. Dark matter is a crucial piece of the cosmic puzzle, and through its exploration, we may gain insights into the laws of physics and the nature of reality itself. Its elusive nature only deepens the mystery, offering a tantalizing glimpse into the unknown. The relationship between dark matter and ordinary, visible matter is essential to understanding the universe. Ordinary matter, composed of atoms and visible to us through the emission or reflection of light, interacts with electromagnetic forces. This interaction allows us to observe its behavior, composition, and movement through the light it emits or absorbs. In contrast, dark matter does not emit, absorb, or reflect light, rendering it completely invisible to our eyes. Despite its lack of direct interaction with light, dark matter leaves behind detectable clues, primarily in the form of its gravitational influence on visible matter. For instance, astronomers studying galaxy clusters have noted that the gravitational effects of dark matter cause galaxies to move in ways that cannot be explained solely by the visible matter they contain. This gravitational influence suggests that dark matter exists in vast quantities, far outweighing the visible matter we can observe. The invisible presence of dark matter is a fundamental mystery that continues to challenge our understanding of the universe, its composition, and the forces that govern its behavior. As we venture further into the unknown, dark matter will undoubtedly remain at the forefront of our quest to comprehend the universe and its hidden realms. Dark matter, often referred to as the unseen force shaping the cosmos, plays an essential role in the formation and evolution of cosmic structures. Acting as an invisible scaffold, it surrounds and supports visible matter, guiding its clumping together into galaxies and vast galaxy clusters over billions of years. This invisible component, though not directly detectable, can be mapped using gravitational lensing, a powerful phenomenon where the light from distant celestial objects is bent by the gravity of dark matter. Through this technique, scientists are able to visualize and track how matter is distributed across the universe, providing invaluable insights into the underlying architecture of the cosmos. Gravitational lensing serves not only as a method to observe dark matter's influence, but also as a key tool in unlocking fundamental questions about the universe. As researchers continue to study the interactions between light and dark matter, they delve deeper into the mysteries of the universe's origin, its present state, and its eventual fate. The study of these forces provides vital clues that guide our understanding of the vast expanse of space and the evolution of galaxies, offering a window into the cosmos like never before. The interplay between dark and visible matter, both in terms of structure and dynamics, shapes the universe at a scale so immense that it's nearly incomprehensible. Another major player in the cosmic drama is the supermassive black hole. These colossal objects, ranging from millions to billions of times the mass of our sun, are more than just astronomical curiosities. They lie at the heart of nearly every galaxy, including our own Milky Way, exerting a powerful influence on the surrounding stars, gas, and cosmic dust. Their gravitational pull dictates the behavior of matter in their immediate vicinity, including the orbits of stars and the formation of complex structures within galaxies. The origins of these supermassive black holes are closely tied to the processes of galaxy formation. As galaxies begin to form, they accumulate mass and gas, which ultimately leads to the growth of a supermassive black hole at their center. Over time, this black hole exerts a profound effect on the surrounding matter, bending the paths of stars and influencing the formation of galactic structures. In some cases, the immense gravitational force drives the creation of accretion disks, a swirling mass of gas and dust spiraling toward the black hole before being devoured. This inflow of matter results in the release of an enormous amount of energy, including X-rays, which are emitted as the material heats up to extreme temperatures. Observing this radiation provides crucial data about the black hole's properties, its growth, and the environment surrounding it. Additionally, the energy radiated by these cosmic giants can have a significant impact on star formation within their galaxies. The shock waves generated by this energy can either stimulate or inhibit the birth of new stars, depending on the intensity of the radiation. These interactions allow scientists to study the intricate processes of galaxy evolution and how galaxies change over the course of billions of years. Supermassive black holes also serve as cosmic benchmarks, helping astronomers measure distances in the universe. By analyzing the light emitted from the accretion disks of these black holes, scientists can infer important information about the rate of expansion of the universe and its overall structure. This ongoing research not only deepens our understanding of how our own galaxy operates, but it also offers a broader perspective on how galaxies evolve across different epochs of the universe. These enigmatic cosmic objects provide a dynamic and fascinating glimpse into the complex relationships between gravity, radiation, and the formation of cosmic structures. Their influence reverberates across the universe, offering essential insights into the forces that govern the formation and evolution of galaxies. Through their study, we uncover a deeper understanding of the intricate processes that shape the cosmos and the extraordinary role these supermassive black holes play in the broader cosmic story. Cosmic light, in its many forms, acts as a messenger, carrying with it valuable information about the distant reaches of the universe. As it travels across vast distances, light from stars, galaxies, and other celestial objects reveals a wealth of data that helps us understand not just the visible universe, but also what lies beyond our ability to directly observe. Different wavelengths of light, such as visible light, ultraviolet, and infrared, provide unique insights into the conditions and properties of the objects emitting them. For instance, infrared light can penetrate dust clouds that obscure our view, revealing hidden regions where stars are being born. This capability allows astronomers to peer into parts of the universe that would otherwise remain concealed from view. Moreover, the way in which light interacts with matter allows scientists to deduce the composition, temperature, and movement of distant celestial bodies. Through the technique of spectroscopy, which involves breaking down light into its component colors, researchers can identify the specific chemical elements present in stars or galaxies. This information reveals not only the physical makeup of these objects, but also their motion through space. One of the most powerful techniques in this regard is the observation of redshift, where the light from distant objects is stretched toward the red end of the spectrum as those objects move away from us. This redshift offers critical clues about the expansion of the universe and the rate at which galaxies are receding from one another. Through the study of cosmic light, we are able to extend our understanding of the universe far beyond what is visible to the naked eye. The analysis of light allows us to detect hidden phenomena such as dark matter and dark energy, mysterious forces that make up much of the universe but do not emit light themselves. By studying how light behaves across vast distances, scientists are able to shine a light on the unseen forces and structures that govern the cosmos, unveiling the hidden layers of the universe that shape its past, present, and future. At the outermost reaches of the observable universe, we encounter some of the most perplexing and exotic objects known to science. Among these are quasars, bright, distant objects powered by supermassive black holes at their cores. Quasars emit immense amounts of energy as they consume surrounding material, making them visible across enormous distances. When we observe a quasar, we are effectively looking back in time, seeing light that has traveled billions of years to reach us. In this way, quasars offer a glimpse of the universe as it was in its early stages, providing critical data on the conditions that existed during the infancy of the cosmos. Another remarkable feature of the universe is the existence of galaxy clusters, vast conglomerations of hundreds or even thousands of galaxies bound together by gravity. These clusters are some of the largest structures in the universe, and their sheer mass can bend and distort the fabric of space itself. At the farthest edges of the observable universe, some galaxy clusters are so massive that they create a gravitational lensing effect, magnifying the light from objects lying behind them. This phenomenon enables astronomers to study distant galaxies that would otherwise remain hidden from view, offering insights into the most distant regions of the cosmos and the early stages of galaxy formation. In exploring these cosmic mysteries, scientists continue to push the boundaries of our knowledge, using tools like gravitational lensing and spectroscopy to observe phenomena that are otherwise beyond our reach. These observations provide an ever-deepening understanding of the universe's complex and ever-evolving structure, revealing the processes that have shaped its growth and evolution over billions of years. Through the study of these distant and exotic objects, we continue to unravel the mysteries of the cosmos, inching closer to a complete understanding of the forces that govern the universe at its most fundamental level. Scientists have long been captivated by the enigmatic nature of the universe, uncovering objects and phenomena that push the boundaries of our understanding. Among these, gamma-ray bursts stand out as some of the most powerful and fascinating events ever observed in the cosmos. These are extraordinarily energetic explosions that occur in distant galaxies, often far beyond the reach of conventional observation. Thought to mark the final moments of massive stars or the violent collisions of neutron stars, these bursts release a staggering amount of energy in mere seconds, far more than the sun will emit over its entire lifetime. The sheer intensity of gamma-ray bursts, combined with their rarity, makes them among the most energetic and mysterious events known to science. At the heart of these cosmic phenomena lies a tantalizing possibility: the existence of dark matter and dark energy, two elusive forces that scientists have long suspected but have yet to fully observe. Though invisible, their influence is undeniable. Dark matter and dark energy pervade the universe, shaping its structure and driving its expansion. Their effects can be seen in the way galaxies form, cluster, and evolve, but the underlying mechanisms remain largely unknown. These mysterious components are at the forefront of astronomical research, their secrets waiting to be uncovered. Each new discovery brings us one step closer to unlocking the mysteries of the cosmos, revealing just how much more there is to explore and understand. As astronomers continue their quest to peer deeper into the universe, their discoveries shine a light on the vast unknown. From the darkest corners of space to the most distant galaxies, the search for knowledge drives the field forward, revealing more astonishing phenomena. It is a journey that captivates both professional scientists and space enthusiasts alike, as the answers to our greatest questions seem to lie just beyond our grasp. The more we learn, the more we realize how much remains to be discovered, how much is waiting for us in the cosmic depths. Pulsars and neutron stars represent some of the most extraordinary and mind-boggling objects in the universe. These cosmic wonders extend our understanding of the universe far beyond what can be seen with the naked eye. To fully appreciate their significance, one must first understand what neutron stars are. They are the remnants of massive stars that have exploded in supernova events, collapsing under their own gravity to form incredibly dense objects. The density is mind-blowing. A single cubic centimeter of neutron star material can weigh as much as an entire mountain on Earth. These collapsed cores are often just a few kilometers in diameter, but contain more mass than the sun itself. Pulsars are a specific type of neutron star, and they possess unique characteristics. They emit beams of electromagnetic radiation, which are generated by the star's rapid rotation and powerful magnetic fields. As the pulsar spins, these beams sweep across space, much like the beam of a lighthouse sweeping across the ocean. When one of these beams happens to point toward Earth, we perceive it as a regular pulsing signal, hence the name pulsar. What makes pulsars even more remarkable is the precision with which they pulse. The timing of these pulses can be so exact that scientists use them as cosmic clocks. By studying the regularity of these pulses, they can uncover vital information about the structure of space-time itself and test Einstein's theories of relativity. Pulsars also provide a unique laboratory for studying extreme physics. The conditions in and around neutron stars far exceed anything that can be replicated in laboratories here on Earth. These environments offer an unparalleled glimpse into the fundamental forces of nature, allowing scientists to study how gravity and matter behave in some of the most extreme conditions imaginable. Additionally, pulsars have played a pivotal role in the discovery of gravitational waves, ripples in spacetime caused by the violent movements of massive objects like neutron stars. By observing the variations in pulsar signals, scientists have been able to detect these ripples, opening a new window into the study of gravitational waves and further enhancing our understanding of the universe. In this way, the study of pulsars and neutron stars bridges the gap between theory and observation. These objects help astronomers unlock the secrets of stellar evolution, the nature of gravity, and the very fabric of spacetime itself. They remind us that even in the vast emptiness of space, there are phenomena that provide invaluable insights into the workings of the cosmos, insights we are only just beginning to explore. Magnetars, another fascinating type of neutron star, offer a wealth of mysteries that continue to challenge our understanding of the universe. These celestial giants are distinguished by their extraordinarily strong magnetic fields, fields that are millions of times more powerful than those found around ordinary neutron stars. The magnetic forces of a magnetar are so intense that they warp the very fabric of space-time, creating conditions that scientists are only beginning to understand. The formation of these magnetic fields and the processes that lead to the creation of such powerful magnetars remain largely a mystery. Understanding how a massive star can collapse into such a dense, small object while simultaneously generating such extraordinary magnetic fields could shed light on many unanswered questions about the nature of stars and the life cycles of the most massive celestial bodies. Magnetars also exhibit incredible bursts of energy, often in the form of X-rays and gamma rays. These flares are not only among the most powerful emissions in the universe, but also highly unpredictable. The causes behind these eruptions remain a subject of intense study, as scientists try to unravel the extreme physics that govern these strange objects. These bursts of energy challenge our understanding of matter and energy under extreme conditions, pushing the boundaries of known physics and encouraging new theories that may one day revolutionize our understanding of the universe. Another intriguing aspect of magnetars is their interactions with the environment around them. The powerful gravitational and magnetic fields of a magnetar can influence nearby stars and gas clouds, potentially affecting the process of star formation. The implications of these interactions could provide key insights into the larger scale processes that shape galaxies and the overall structure of the cosmos. By studying magnetars, scientists are not only uncovering the mysteries of these fascinating objects, but also unlocking clues to the broader processes that govern cosmic evolution. Despite their relative rarity, magnetars hold the potential to answer some of the most profound questions in astrophysics. Their extreme properties make them natural laboratories for studying the behavior of matter, energy, and magnetic fields in conditions that cannot be replicated on Earth. Each new discovery related to magnetars brings us closer to understanding the fundamental forces of the universe, opening new pathways of inquiry into the deepest regions of space. Cosmic phenomena, such as the bursts of energy from gamma-ray bursts or the mysterious behavior of dark matter, often serve as a reminder of how little we truly know about the universe. These unique events have the power to disrupt established scientific models and theories, forcing researchers to reconsider long-held assumptions. For example, the initial models of galaxy formation were based primarily on visible matter, yet the discovery of dark matter and dark energy has fundamentally reshaped our understanding of how galaxies form and evolve. As scientists continue to explore the unknown, each new mystery uncovers yet more questions, pushing the boundaries of knowledge and inspiring future generations to continue the search for answers. However, a series of extraordinary and perplexing observations of galaxies behaving in ways no one expected unveiled the existence of forces that were invisible to our instruments, forces that led to the groundbreaking concept of dark matter. This enigmatic substance makes up a large and crucial portion of the universe, yet it remains completely undetectable by our current technology. Dark matter is a cosmic mystery, an invisible foundation that influences the universe on a scale we can barely grasp. The more we study, the more we realize how much of the cosmos operates beyond the reach of direct observation. These startling discoveries have a powerful effect on the scientific community. They challenge and complicate the established understanding of the universe, forcing astronomers, physicists, and astrophysicists to rethink and often completely overhaul existing theories. Each new anomaly, each discovery that contradicts our models, is like a puzzle piece that refuses to fit, pushing researchers to either modify their current frameworks or, in some cases, create entirely new ones. Take, for example, the collision between neutron stars. When these dense, extraordinary objects collide, they generate gravitational waves so powerful that they are detectable across vast stretches of space. These waves give us a glimpse into the very fabric of the universe, forcing scientists to refine their understanding of gravity and the fundamental forces that shape the cosmos. In many ways, these remarkable phenomena also expose the limits of our current observational tools. One of the most intriguing examples of this is the discovery of fast radio bursts, FRBs, brief, intense flashes of radio waves emanating from distant galaxies. These enigmatic signals defy explanation, and in doing so, they present a pressing challenge to researchers. How can we improve our technology to better monitor and interpret such elusive cosmic messages? Every new discovery, no matter how baffling, opens a door to technological innovation. It drives the development of more sensitive instruments, the creation of advanced simulations, and the constant refinement of techniques to understand the behavior of these cosmic entities. As scientists work to decode these strange and complex phenomena, they are inevitably drawn to confront some of the most fundamental questions about the nature of reality itself. The universe, they are reminded, is not a static, predictable machine, but a vast, ever-evolving system. This ongoing process of discovery, full of unexpected twists and turns, highlights the dynamic relationship between observation and theory. Each breakthrough and each mystery reminds us that the universe is constantly revealing new secrets, secrets that demand we update our understanding and continue pushing the boundaries of knowledge. The unpredictable nature of cosmic events fosters a deeper inquiry, an insatiable curiosity that propels humanity into a relentless pursuit of answers. Each discovery, no matter how strange or unexpected, sparks new questions. And it's this drive to uncover the unknown that fuels the ever-expanding field of astrophysics and cosmology. One of the most revolutionary ideas in this quest for understanding came from Albert Einstein's theory of relativity. This groundbreaking theory transformed how we perceive space and time, revealing that these two concepts are not separate, independent entities, but are intricately linked, forming a four-dimensional fabric known as space-time. This relationship between space and time has profound implications for how we understand the universe. Relativity tells us that mass and energy warp the very fabric of space-time itself, shaping the cosmos in ways that are often invisible to us, but essential to its structure. When we begin to consider the edges of the universe, those far-flung regions where the laws of physics seem to lose their grip, Einstein's theory becomes even more critical. The idea that space-time can be warped by massive objects, such as galaxies and black holes, has far-reaching implications for our understanding of these remote, mysterious realms. For example, if we consider the universe's expansion, a concept that Einstein's equations helped bring to light, it's akin to inflating a balloon. As the balloon expands, the surface stretches, causing the points on the surface to move farther apart. This analogy helps us visualize how galaxies on the distant reaches of the universe are moving away from us, their light stretching and redshifting as they recede into the cosmic expanse. But this expansion doesn't just challenge our understanding of distance, it also forces us to rethink the very nature of time. Near massive objects, time itself behaves differently. A clock on Earth ticks at one pace, but an observer near a black hole, for example, would experience time passing much more slowly. This phenomenon, known as time dilation, illustrates how relativity reshapes our perception of both time and space. It forces us to confront the idea that time is not a universal constant, but a variable that can bend and stretch depending on where you are and the gravitational forces at play. The very notion of the universe's edge is also deeply influenced by relativity. The boundaries of the cosmos might not be as straightforward as we once thought. Instead of a definitive physical edge, we may be dealing with the limits of our observable universe. Beyond that, space and time might behave in ways that are fundamentally unknowable. The universe could continue expanding indefinitely, with no true boundary, no end. And, depending on its curvature, the shape of the universe may not be flat, but a complex, dynamic structure that constantly evolves. In light of these possibilities, the concept of the universe's edge becomes less about a physical location and more about an ever-expanding horizon that constantly moves further out of our reach. The fabric of space-time stretches ever outward, propelled by forces we are only beginning to understand. Through Einstein's lens, we see that the universe is not just a static backdrop of stars and galaxies, but a dynamic, ever-changing entity that is shaped by the mass and energy within it. But the mysteries don't end there. In the far reaches of the cosmos, regions where time and space seem to fold back on themselves, there are even more mind-bending possibilities. Imagine for a moment a reality where time is not a simple linear progression. Instead, it is a complex web of loops and folds, where events might not follow a straightforward path but could repeat, overlap, or even run backward. These folds in time could create loops where the future influences the past and vice versa. In such a scenario, the very concept of cause and effect would be turned upside down. If time loops truly exist, they could open the door to a form of time travel. Imagine being able to revisit a past event or witness a future outcome that would otherwise be inaccessible. Such time loops might even allow for interactions between different points in time, where information, or even people, could move freely across the folds, creating entirely new possibilities for understanding and exploring the cosmos. However, this also introduces a number of paradoxes. If someone were to travel back in time to change an event, could they create an alternate timeline, or even erase their own existence from the past? These questions raise deep philosophical and scientific dilemmas that are yet to be fully addressed. Furthermore, the idea of time-time folds could radically alter our view of cosmic phenomena. Imagine that a supernova, which we observe today, might not actually be happening in the present moment at all. Instead, the light we are seeing could be from an event that took place long ago, but the effects of that explosion might ripple forward in time, influencing future events. These concepts are tantalizing and potentially transformative, but they remain speculative. Our current understanding of physics doesn't yet offer a clear mechanism for how such phenomena could exist, let alone be traversed, without causing catastrophic disruptions to the fabric of reality. Ultimately, these anomalies challenge our understanding of time and the very structure of the universe. While we operate under the assumption that time is predictable and linear, these cosmic mysteries suggest that there may be deeper, hidden layers of reality that we have yet to uncover. These unknowns continue to beckon us forward, urging scientists to probe deeper into the nature of space, time, and the very fabric of existence itself. The idea of alternate dimensions further complicates this picture, expanding our view of the universe beyond the familiar 3 dimensions of space and 1 dimension of time. Traditionally, our understanding of the universe has been grounded in this 4-dimensional framework, but the existence of alternate dimensions, places where different rules of physics might apply, forces us to reconsider the limits of our knowledge and the nature of reality itself. Could these dimensions be home to entirely different laws of physics? Or could they hold the key to unlocking the greatest mysteries of the universe? This is a question that will continue to drive the exploration of the cosmos in the coming decades. However, when we delve into the idea of alternate dimensions, we begin to explore realms that transcend the boundaries of human perception, suggesting that reality may hold far more than what we experience through our senses. Imagine, if you will, our 3-dimensional world as a flat surface, much like a sheet of paper. Now, consider the possibility that there are other dimensions, hidden from our view, coiled within this paper. These dimensions could each be a distinct layer with its own unique properties and laws governing the behavior of matter, energy, and space. These additional dimensions could act as gateways or pathways, connecting distant regions of the cosmos. What we perceive as the farthest reaches of our universe might not be the end of the road at all. Instead, they could be the threshold between our universe and others, offering an interface with realities that exist beyond our comprehension. The study of these alternate dimensions opens up new ways of thinking about the universe and its many mysteries, particularly phenomena that have long puzzled scientists, such as dark matter and dark energy. Dark matter and dark energy represent two of the most elusive components of the universe, making up a vast majority of its content, yet remaining hidden from direct detection. If alternate dimensions exist, they might offer explanations for these strange phenomena, potentially influencing gravitational forces or enabling interactions that occur outside the scope of our conventional understanding. In this way, the boundaries of our universe could be seen not as hard limits, but as entry points into these hidden realms. By considering the possibility of alternate dimensions, scientists are not only deepening our understanding of the cosmos, but are also beginning to ask more profound questions about the nature of existence itself. This line of thought leads us naturally to the concept of the multiverse, an idea that suggests there may be an infinite number of universes, each with its own set of physical laws. The implications of this are staggering. If such universes exist, each could operate according to different principles, where gravity behaves differently or the speed of light is not a constant. What would it mean for us and for our understanding of physics if we were not alone in our universe, but part of a vast interconnected multiverse? Such a shift in perspective could alter our very conception of what it means to be part of the cosmos, inviting us to reconsider everything we think we know about the universe, existence, and reality itself. At the very edge of the observable universe, where light takes billions of years to reach us, we encounter phenomena that challenge our understanding of time, space, and reality. When scientists observe distant galaxies, they are not merely witnessing what is happening right now. Instead, they are looking back in time, seeing the universe as it was billions of years ago. This delay in the transmission of light offers a glimpse into the distant past, highlighting the complexities of understanding time itself. In this sense, our perception of the universe is not continuous, but more akin to snapshots, each one a frozen moment in the ongoing cosmic drama. One of the most fascinating theories that emerges from these observations is the concept of cosmic inflation. This theory proposes that in the moments immediately following the Big Bang, the universe expanded at an incredibly rapid rate, reshaping the very fabric of space and time. As we observe distant galaxies moving away from us at increasingly faster speeds, we are faced with the question, what does it mean for space itself to be expanding? Rather than viewing the universe as a static entity, we are now led to think of it as an ever-expanding expanse, where even the distances between galaxies are stretching over time. Distant cosmic phenomena such as supernova, the explosive deaths of stars, offer further insight into the complex and cyclical nature of the universe. These cataclysmic events not only illustrate the life cycles of stars, but also suggest a deeper truth. The universe is filled with intricate processes, cycles of birth, death, and rebirth that stretch far beyond our immediate understanding. Our current experience of the universe may be but a brief moment in this grand cosmic cycle. The discovery of dark matter and dark energy, two phenomena that make up the vast majority of the universe, yet remain undetectable through direct observation, has fundamentally reshaped our understanding of reality. Dark energy, which appears to drive the accelerated expansion of the universe, challenges our traditional view of a static cosmos and invites us to imagine a universe that is constantly changing, evolving, and expanding. Similarly, the study of the cosmic microwave background radiation, the afterglow of the Big Bang, provides a glimpse into the earliest moments of the universe and pushes the boundaries of our understanding about the nature of singularity. In this way, the discoveries made at the very edge of our universe are not just scientific revelations, but also philosophical ones. They push us to reconsider fundamental concepts such as time, space, and existence itself. The more we learn about the universe, the more cosmos is far more complex, far more mysterious than we could have ever imagined. And in this realization lies an invitation to think beyond the familiar, to explore the vast unknown, and to expand the boundaries of human knowledge. The discoveries we make in space provoke deep philosophical questions that resonate with our understanding of existence. As we peer into the depths of the cosmos, observing distant galaxies, planets beyond our solar system, and the very structure of the universe itself, we are forced to confront profound questions about our place in the grand scheme of things. What does it mean to be human in such a vast and seemingly infinite universe? Are we truly alone, or do countless other forms of life exist, each seeking the same answers to these existential questions? The realization that there may be other beings out there in distant galaxies raises the possibility of shared consciousness or experience across the universe. Could we be part of a greater cosmic community, united by our shared curiosity and quest for understanding? Or are we in fact isolated, each left to contemplate the mysteries of the universe on our own? At the same time, the study of enigmatic phenomena like black holes forces us to reconsider our basic notions of reality. Black holes, with their incredible gravitational pull, warp both space and time, creating conditions that defy our usual understanding of physics. If time can be bent, as it is around these mysterious objects, what does that mean for our understanding of beginning and end? Are we simply fleeting moments in an eternal cosmic dance? Or do we hold a more significant role in the unfolding story of the universe? Furthermore, the concept of the multiverse introduces another layer of complexity to our understanding of existence. If there are infinite parallel universes, each one representing a different possible outcome, what does this say about the nature of free will? If every decision we make plays out in another universe, what truly defines our choices and experiences? Are we unique, or are we simply one version of countless others, each making similar decisions in parallel realities? These questions compel us to reflect on the nature of knowledge itself. How much can we truly understand about the universe, and how much of it will always remain beyond our grasp? With every discovery we make, we are reminded of the limits of human understanding, and yet our thirst for meaning persists. The universe, in all its complexity and mystery, continues to inspire both awe and humility. Ultimately, the exploration of space is not just about expanding our scientific knowledge. It is about deepening our understanding of life, existence, and our place in the grand tapestry of the cosmos. Each new discovery, each new revelation about the universe serves as a stepping stone in the ongoing journey to understand the world around us. Throughout history, the quest to understand the cosmos has been driven by the same curiosity that first led ancient civilizations to gaze at the night sky. The Babylonians, Greeks, and many others spent countless hours observing the heavens, developing early models of celestial mechanics and calendars that would lay the foundation for modern astronomy. Though their models were not perfect, they provided the building blocks for a deeper understanding of the universe. The invention of the telescope in the 17th century marked a pivotal moment in this journey. For the first time, astronomers like Galileo were able to peer into the depths of space and observe phenomena that were previously invisible to the naked eye. His discovery of moons orbiting Jupiter directly challenged the geocentric view of the universe, supporting the heliocentric model of the solar system proposed by Copernicus. This was a paradigm shift, a radical rethinking of our place in the universe. As technology advanced, so too did our ability to explore the cosmos. In the early 20th century, the discovery of galaxies beyond the Milky Way revealed that our galaxy is just one among billions, vastly expanding our understanding of the scale of the universe and our place within it. What we once thought of as the entire universe turned out to be just a small corner of a much larger, more intricate cosmos. Each new discovery pushes the boundaries of what we know, leading us to ask bigger questions about existence, reality, and our role in the grand cosmic scheme. In this way, the journey of exploring the universe is not just about uncovering the unknown, but also about discovering who we are and what it means to be part of this awe-inspiring cosmos. The advancement of scientific instruments, particularly powerful ones like radio telescopes, has allowed researchers to peer into the distant past of the universe, capturing the faintest echoes of its earliest moments. These instruments have opened up new windows into the vast and mysterious cosmos, shedding light on the origins of the universe itself, including key events such as the Big Bang. Each new discovery, whether it be the detection of cosmic microwave background radiation or the observation of far-off galaxies, contributes a vital piece to the puzzle of understanding the universe's birth and evolution over time. The 21st century saw one of the most groundbreaking revelations in the form of gravitational waves. This discovery unlocked a new frontier in astrophysics, enabling scientists to observe phenomena that were once beyond the realm of possibility, such as the merging of black holes and neutron stars. These phenomena, which had previously been completely invisible, are now observable thanks to sophisticated instruments that can detect the ripples in spacetime caused by their collision. The accumulation of such discoveries, each one building on the last, not only deepens our understanding of the cosmos, but also drives innovation across various fields of technology. From advancements in material science to breakthroughs in telecommunications, the effects of these astronomical discoveries echo throughout other areas of human endeavor. Today, our understanding of the universe is a vibrant and ever-evolving tapestry. It is woven from centuries of scientific inquiry, with each new thread of discovery creating a more detailed and intricate picture of the cosmos. This ongoing exploration fosters an unceasing quest for knowledge and ignites the imagination, suggesting that even more mysteries of the universe await unraveling in the future. Each historical breakthrough, no matter how monumental, becomes a stepping stone for the discoveries yet to come. It sets off a chain reaction across generations, sparking new questions, new methods of exploration, and fueling a shared curiosity that has defined humanity's engagement with the universe since the dawn of civilization. Mapping the farthest reaches of space is no simple task. It is an endeavor that requires the use of advanced techniques and cutting-edge technologies. One of the most essential tools for this work is the telescope. Large optical telescopes, often placed at high altitudes to avoid interference from Earth's atmosphere, provide astronomers with the clearest possible views of distant galaxies, nebulae, and other cosmic phenomena. These high-powered instruments minimize the distortion caused by atmospheric disturbances, allowing for observations of objects that are billions of light years away. Additionally, telescopes equipped with sensitive cameras are able to capture stunning images of the universe's most distant objects, revealing hidden details that were once beyond reach. Radio telescopes have also become indispensable in the study of the cosmos. These instruments capture radio waves emitted by celestial objects such as pulsars, quasars, and galaxies. The signals they collect, often faint and distant, provide astronomers with crucial data about the structure and behavior of the universe, even in cases where visible light from these objects is obscured by cosmic dust or other interstellar phenomena. By analyzing these radio waves, scientists can gain insights into the composition and movement of objects that are otherwise impossible to observe with optical telescopes alone. Spectroscopy, another essential technique in cosmic exploration, involves studying the light emitted or absorbed by distant stars and galaxies. This process enables scientists to determine critical information about the composition, movement, and temperature of these objects. By analyzing the spectra of light from these distant bodies, astronomers can map the distribution of various elements throughout the universe, helping to uncover how these elements interact and form larger cosmic structures over time. One of the most fascinating phenomena in the universe is gravitational lensing. When massive objects, like galaxies or clusters of galaxies, bend the light from objects behind them, they act as natural magnifying glasses. By studying these distortions, astronomers can learn about the mass, shape, and other properties of the foreground objects causing the lensing effect. More remarkably, this technique allows for the detection of objects that would otherwise be too faint to be observed, revealing hidden parts of the universe that would otherwise remain beyond our reach. Cosmic surveys, a vital tool for modern astronomy, compile data from multiple sources to create large, comprehensive datasets that map the positions, brightness, and distances of millions of galaxies. These surveys are essential in helping scientists understand the large-scale structure of the universe, from the way galaxies are clustered together to how they evolve over time. Through these surveys, astronomers are able to paint a broad and detailed picture of the cosmos, one that continually evolves as new data is collected and new discoveries are made. As technology progresses, the tools we use to explore the universe continue to improve. Our ability to unlock the secrets of the cosmos, to see farther and deeper than ever before, grows stronger with each new development. These advances not only enhance our understanding of the universe, but also promise new discoveries that will likely reshape our understanding of everything from the fundamental laws of physics to the nature of life itself. Interestingly, methods traditionally used in cartography, the science of mapping the Earth's surface, also play a pivotal role in modern cosmic exploration. These techniques help scientists map distant celestial bodies such as planets, moons, and entire star systems. Cartographers working in space utilize data collected from telescopes, spacecraft, and satellites to create detailed maps of these faraway worlds. These maps provide essential information about the topography, surface materials, and environmental conditions of these bodies, which are crucial for planning missions, navigating spacecraft, and ensuring successful communication with exploration teams. For example, consider the mission to Mars. Scientists rely on high-resolution imagery obtained from orbiters to create comprehensive surface maps of the red planet. These maps offer a detailed look at features such as ancient riverbeds, volcanic formations, and other geological structures that reveal insights into Mars' history and climate. These maps are invaluable tools for guiding rovers across the Martian surface, ensuring that they reach their intended targets while avoiding potential hazards that might jeopardize the success of the mission. Similarly, when looking at our own galaxy and the galaxies that lie beyond, cartographic methods allow astronomers to map the distribution of stars, gas, and dust throughout these vast regions. Understanding how these elements are arranged and how they move through space helps scientists track the behavior of cosmic structures over time. Through this process, we are learning not only how individual stars and galaxies evolve, but also how the large-scale architecture of the universe itself is shaped. In this way, space cartography has evolved from a simple tool for mapping terrestrial landscapes into a sophisticated and vital science that enables us to visualize, understand, and navigate the infinite expanse of space. As technology continues to progress, these cartographic methods will only become more refined, allowing for even more detailed and accurate representations of the universe that continue to push the boundaries of human knowledge. Star mapping, too, has undergone a remarkable evolution, driven by significant technological advancements. In the past, astronomers relied on manual observations and the limited capabilities of telescopes to chart the stars. Today, however, we have access to large-scale telescopes equipped with advanced sensors that can collect vast amounts of light and data, far beyond what was possible in the past. These new instruments allow us to detect objects that were once invisible, such as faint stars, distant galaxies, and even exoplanets orbiting other stars. Furthermore, the integration of artificial intelligence into astronomical research has revolutionized the field of star mapping. AI-powered algorithms can now analyze enormous amounts of data in record time, identifying patterns and anomalies in stellar formations that human astronomers might miss. This not only speeds up the process of discovery, but also ensures that star maps are more accurate and reliable than ever before. The combination of advanced telescopes and artificial intelligence has opened up new possibilities for exploring the universe, allowing us to create star maps that are more detailed, comprehensive, and precise than ever before. In conclusion, the mapping of the universe from distant galaxies to individual stars is an intricate and evolving process. It involves the use of a diverse array of techniques, technologies, and methodologies that come together to form a cohesive understanding of the cosmos. With each new development in astronomy, our ability to explore and understand the vastness of space grows stronger, bringing us ever closer to unraveling the many mysteries that lie beyond our reach. The journey of cosmic exploration is far from over, and with every discovery, we inch closer to answers that will continue to inspire future generations of scientists and explorers. Satellite missions like those led by the European Space Agency, ESA, and NASA have been instrumental in advancing our understanding of the universe. These cutting-edge satellites, equipped with sophisticated spectrometers and a range of specialized instruments, offer a unique vantage point above Earth's atmosphere. This positioning eliminates the distorting effects of the atmosphere, providing scientists with clearer, more accurate data for studying distant celestial bodies. These tools enable the collection of data that would otherwise be impossible to obtain from the surface, resulting in more precise star maps and a deeper understanding of the cosmos. Additionally, the rise of citizen science projects has opened new avenues for public engagement. These initiatives harness the collective power of individuals, amateurs, and enthusiasts from around the world. By analyzing data captured by professional observatories, the public contributes to the ongoing efforts to map the stars. This democratization of science broadens the scope of data collection, while also fostering a sense of shared purpose and enthusiasm for astronomical discovery. As a result, these collaborative projects not only enhance scientific knowledge, but also deepen the public's connection to the universe. The evolution of star mapping is a remarkable fusion of powerful telescopes, cutting-edge technology, and community involvement. Each technological leap brings us closer to a more intricate and detailed map of the cosmos. As these advancements unfold, they offer the promise of unlocking the many mysteries that lie beyond our world. These new maps help reveal the complex structures of the universe, providing clues to its origin, evolution, and perhaps even its ultimate fate. One of the most profound areas of exploration in modern astronomy focuses on the edges of the observable universe. This region, defined by the limits of what we can currently detect and study, presents tantalizing questions about the true nature of the cosmos. What lies beyond the boundaries of known space? How do dark matter and dark energy influence the universe's expansion? The quest to answer these questions drives much of the current research in cosmology. The focus on these unexplored regions is fueled by a combination of human curiosity, technological capabilities, and the promise of groundbreaking discoveries. As new instruments and telescopes are developed, they open up previously inaccessible areas of space. For example, advanced observational technologies can detect faint signals from galaxies billions of light years away, allowing scientists to peer deeper into the universe than ever before. These breakthroughs inspire further exploration, as new data often challenges our understanding and forces us to refine existing theories. International collaboration plays a key role in these endeavors. Teams of scientists from around the globe share data, findings, and resources, leading to a more comprehensive understanding of the universe's vastness. These collaborative efforts often prioritize projects based on their scientific significance, technological feasibility, and the availability of funding. High-profile missions, such as those focused on studying cosmic microwave background radiation or exploring the early universe, tend to capture widespread attention and resources. These projects not only advance our understanding of the universe's origins, but also ignite the public's imagination. Ultimately, the prioritization of research in the universe's unexplored regions is shaped by a complex interplay of scientific inquiry, technological innovation, societal interests, and funding considerations. Each new discovery adds a new layer of complexity to the puzzle, ensuring that the mysteries of the cosmos will continue to captivate and inspire future generations of scientists and thinkers. Collaboration between physicists and astronomers has become an essential aspect of modern scientific research. These two fields, while distinct, often work in tandem to deepen our understanding of the universe. Many of the phenomena observed in space, whether it's the behavior of distant galaxies or the nature of black holes, require the application of physical principles to be fully understood. For instance, once astronomers identify distant cosmic objects, physicists employ theoretical models to explain their behavior, interactions, and evolution over time. A particularly exciting area of cross-disciplinary collaboration is the study of gravitational waves. First detected by specialized observatories created by physicists, these ripples in space-time have opened up an entirely new way of studying the universe. Gravitational waves provide insights into dramatic cosmic events, such as the collision of black holes. By combining observational data with theoretical models, scientists can explore fundamental questions about gravity, space-time, and the very fabric of the cosmos. Large-scale scientific projects, such as space telescopes and particle accelerators, frequently bring physicists and astronomers together to achieve their shared goals. The development of tools to detect exoplanets, for example, requires a deep understanding of light physics, as well as innovative observational strategies to interpret data. In these efforts, physicists help design the technology, while astronomers focus on its application in the field. This collaboration pushes the boundaries of both planetary science and astrobiology, offering new insights into the potential for life beyond Earth. Computer modeling and simulations represent another powerful intersection between these fields. Physicists create detailed simulations of cosmic events, helping astronomers predict and visualize complex phenomena such as galaxy formation, the behavior of dark matter, and the life cycle of stars. These virtual experiments provide valuable insights into cosmic processes, refining existing theories and inspiring new hypotheses. Conferences and research initiatives that bring together physicists, astronomers, and other experts provide important forums for the exchange of ideas. These gatherings foster the development of innovative ideas and groundbreaking observational techniques, further bridging the gap between theory and observation. By working together, these two disciplines enhance our understanding of cosmic phenomena and inspire new ways of thinking about the universe. Educational institutions, too, play a pivotal role in advancing our understanding of the universe. Universities and research centers act as intellectual hubs where curiosity and rigorous inquiry meet. In these institutions, students and researchers have access to state-of-the-art technology, such as powerful telescopes and particle accelerators, enabling them to explore the farthest reaches of space and the most fundamental aspects of matter. From the faint light of distant galaxies to the smallest particles that make up the universe, these institutions provide the tools necessary for uncovering the cosmos's many secrets. Moreover, educational institutions encourage interdisciplinary collaboration, allowing ideas from fields like physics, mathematics, and even philosophy to enrich our understanding of the universe. These cross-disciplinary partnerships often lead to groundbreaking discoveries that expand our theoretical frameworks and deepen our understanding of the cosmos. By combining theoretical exploration with practical experimentation, universities foster a holistic approach to studying the universe's vast mysteries. Beyond the confines of academia, educational programs and public outreach initiatives raise awareness and inspire the general public to engage with astronomical discoveries. These programs help demystify complex scientific concepts and invite people to ponder the mysteries of the cosmos, encouraging a broader societal interest in space exploration. In this way, educational institutions are at the forefront of the intellectual movement to understand the universe's limits. Through research, collaboration, and public outreach, they illuminate the path to uncovering the vast unknowns that lie beyond our planet, continually pushing the boundaries of human knowledge. The work being done today will undoubtedly pave the way for future generations to unlock even greater secrets about the cosmos.